Hello everybody, how we doing? I forgot to get the music going, so let's do that. Get a bit of Stone Rebel going. But yeah, welcome. How's everyone doing? What's going on? There we go. To sort my levels out. So, last stream, we actually sort of got the new version of HCC in because it basically fixed the whole texture addressing or the texel addressing stuff, which we're going to be using for the occlusion buffer. So, and the stream before we did the first bit of the occlusion buffer, and this stream we're going to finish it. So that's the plan basically. So I guess we'll quickly go over the occlusion buffer again as we build it. And then I don't know what we should do after that. If we've got spare time, we should probably look at making this model have chunks, well not chunks, clusters or something, I think. Because I want to prepare for the thing we're doing next stream. Hey Eternal Divine Fox. Hey Kraz, welcome guys. Pretty good. Awesome. Yeah, not bad. Just yeah. Just been chilling. Had a chill day yesterday. It's pretty moody weather, so just stayed indoors and watched TV. Chilled with the wife and baby. But yeah, things have been going good though. Basically just exercised a whole bunch, you know. So it was a lot of fun. Yeah, so this is the plan we're executing on. Yeah, so I've also done another plan. Because this just is effect. Oh, one of those. A bit too far up. This one essentially just allows us to to not put a sphere in a screen tile if it's occluded. It was definitely occluded by another sphere or group of spheres. But I've been thinking about how we're going to be doing lighting and shadows, and I've written up another plan on the Discord as well. I don't know if this is going to be compatible with the occlusion buffer that we're writing, but I want to finish the occlusion buffer purely because by doing this occlusion buffer, we've basically fixed a design problem in the HCC compiler, and it still might be useful. So I do want to finish it, and it's good just to see like what sort of performance it gives us, and stuff like that. It's always good to just finish things. Let the spheres move between bins. Yeah. Well, they've been binned every frame, so they're going to be moved between the bins. That's for sure. Sure. So we did this one. Well, we're binning them into. We've written the shader at least, but we've not triggered it. So let's go to that. Source, graphics. Right. So here we've commented this out. So we've got an occlusion texture. So I guess I might describe exactly how the system works, right? Again, because it's good to recap. So we've created an occlusion texture. It's full screen with n MIP levels. They go up to 1 by 1 pixel basically. So we create a full MIP chain. We dispatch over all spheres. Each thread gets the inner axis line bounding box of a sphere. So let's get MIP1 up and draw it. In screen space. And then atomic mins a single depth pixel to a MIP level where the ABB is less than 2 pixels. So we kind of did some drawings here before, when I described it before. So yeah, something like this. So you get your sphere, you get this sort of inner axis line bounding box, project that onto the view, the near clip plane, bring that to screen space, right? So you get your bounding box on the screen, and then here's the maximum depth value. The max depth value, and you sort of so basically that depth value should technically be encoded into all of these pixels here, but that takes a lot of effort. We don't want to be doing that, because if we've got a whole bunch of spheres and they're all doing atomic mins to a whole bunch of overlapping pixels, you start to get like this, the different compute units might have to synchronize with other compute units to sort of deal with which one with the atomic values or something like that. So often if you use atomics, you got to be careful making sure there's not two threads or two different compute units overlapping, basically. Otherwise it has to synchronize through the cache, the L1 and L2 caches or something like this. So to avoid that, to minimize that problem, what we're doing is we have a full MIP chain. So this is full screen resolution. This one here. This is half resolution, quarter resolution, and you go all the way down until you get to 1 pixel, 1 by 1 pixel. So when you have a sphere, we're just going to write a single pixel for it. And so you'll be like, so this sphere, it takes up, let's say it takes up like 80 pixels. You'll go down the MIP chain, half it, until it reaches a resolution where it's 1 pixel, and then it'll find the location and write a single pixel there. And it'll write the depth value there, right? So there's only one write happening. It's happening over all these different textures. So the overlap should be quite kind of minimal. And then what we can do after that, so that's basically describing this shader here. So we reduce the overlapping atomic mins because we've got these MIP levels essentially, and we only write 1 pixel. So if there is an overlap, it's hopefully not as bad. So we've written that shader now, so just got to plug that one back in, and then the next two shaders are basically propagating the values between the MIP levels, because when you write a pixel there, this might have a depth of 35, but then this could overlap. Something like this. This might overlap all these pixels here, right? In the highest resolution or something. And this one originally might have a value of 70 in there, and then you want to like min it. So you want a value of 37 to be placed, or 35 to be placed in all of these, for instance, at minimum. So you min. So you propagate the values down, then back up, and min them against each other. That's what we need to do. That's the basic gist of things, of this occlusion buffer. So the idea is it's just a rough occlusion. When you read a pixel, and you get back a value of 35, it doesn't mean there isn't anything in front of it at 30 units away, right? That could be true, but it means there's nothing definitely behind it at 40, right, or 36. That's the idea. Hey Sockham. Yeah, doing good, man, doing good. How you doing? Good to see you. By the way, I subbed today to check if I could learn something from 3D Engine. Awesome. Yes, Engine, it's a game. Yeah. So the joke is, right, so I say it's a game without an engine, but the joke is that it's an engine without a game, because that's kind of true at the moment. But we'll get there. So we're building out the core, little bits of core foundation. We've got things sort of broken up into like little subfolders, like Um, and so we've built like a GPU layer, a UI. We've done windowing and input sort of game controllers and stuff. Yeah, that's what we got done right now. Um, oh, and obviously the core utilities for like memory allocation and stuff, and arrays and hash table. Um, but now we're doing the sort of the 3D R&D. Yeah, and then after that we'll probably just build some tooling and obviously think of the game, because we after that we kind of have a nice foundation where we can prototype, I think. So that'd be proper cool. So let's try and get this shader hooked in and see if we can actually visualize this information, because it's all well describing it, but it might go over a bit of people's heads when you start to see it. Make a little bit more sense. Oh, and also, I really appreciate the sub there, Eternal Divine Fox. Appreciate it. Yeah, if you have any questions about like the code or any want to see, yeah, just feel free to open up any discussion in the Discord or something. We also have the VODs on the VOD channel, so you can go and find the stream where it's been implemented in there of you as well. Cool. So where is the occlusion? So we just search for occlusion. So we've got the texture with a load of MIP levels. This clears it to a value of positive infinity, I think. So let's enable this, and hopefully it doesn't blow up my machine. So this is just essentially, yeah, it clears it to the highest depth value. We don't have floating point atomics, so you got to do that. So let's see if it clears. And what we're going to do is we're going to hop into RenderDoc probably. Let's run it. Oh, it crashed. Sync resource render frame 538. 538. Base MIP ID? Why isn't that sorted out? Oh, did I not create all my... Right, let me not undo all this. Right, let's bring this back. Oh, I need this for loop again. So we need to create all the texture views. GPU, texture, view initialize, occlusion, texture, view. So we need to have one texture view for each MIP, because you cannot select a MIP level in the shader. You have to have a separate kind of texture for each of those, in a sense. It's a separate descriptor. Oh. The base, the one we're aliasing is this guy. So MIP levels 1. Oh, sorry, base MIP levels will be base MIP level. And you have 1 MIP level. And then 0, 0 for array layers. 0 just means automatic. Okay, so if this is the first one, so we get back a GPU resource ID. If it's the first one, if base equals 0, we'll ggfx dot occlusion base ID. So the way that we're relying on some sort of behavior here. Every single time we call this is just going to be the same like all of our descriptors are in a row. So we have a pool of let's get back one. So we have like a pool of resources, in a sense. So when we make a new texture, we'll get this one. We make another one, we'll get that one. We make another one, we get that one. Make another one, we'll get that one. So they all get allocated one after the other. We haven't done the code that destroys resources yet. So if we destroyed this one, like, we won't have that behavior anymore where it puts one after the other, but we'll have to solve that problem when we add that feature if we do. So right now we're relying on that behavior, and we have a sort of a base ID, and that's the first one. And that way when we pass the resource index up into the shader, we can say, okay, the base MIP is here, this is MIP 0, and then the next one will be MIP 1, the next one will be MIP 2, and this will be 2, this will be 3, this will be 4. So you can basically do 0 plus whatever MIP you want, and you get your texture out. So that's what we're relying on here. So this is going to clear each MIP level and do the width and height stuff. All good. Okay. Let's fire that up. Right, so we're clearing a whole bunch of them. Can you see how we've got all these occlusion clears now? Right, so it's already... It's interesting how... I don't know what's happened today. Maybe it's because we're streaming, I don't know. But this always used to be a flat 0.4 ms for a clear. 0.04 ms. And it's all quite noisy. I'm not sure if I can understand why that is. Oh well. Hey, not so red. How's it going? Good to see you. F crashed. We're still here. We're still here. What are you talking about? Timelines, bitrate seems fine. Must be your end. Why not connect it to Ethernet? Because it's in my work PC. And it's just effort to keep changing the cable. The Wi-Fi works fine. Wi-Fi is not really a problem. But hey there, Drots. Welcome back. Post Iron Anil. Have you ever tried to play with a GPU emulator? Like emulating the simplest GPU? There's plenty of projects which emulate simple CPUs, but no such GPU projects. Yeah, I guess you could probably try and emulate AMD, like RDNA, because they do have an open source ISA, right? RDNA 3 now, ISA, so you can get access to that. You can look at the PDF. It's really good read. You should actually read these things. You can learn a whole bunch about how the GPUs work. And you could implement an emulator for it. But I don't know, I'd rather program for one at the moment. But yeah, if you're definitely learning about things, maybe it's good to run emulator. I think there is already a project out for that, if you look around hard enough. You have to be more specific with your searches. See, it's already quite a lot to sort of clear those occlusion textures. That's already not that great. Why is it so much? Like, why is it so much? Yes, this is part of the problem, hey Sockham. Searching on Google is terrible. So you always have to put in specific words to get to find it. find stuff you want nowadays. But yeah, I just googled that. Like, if you just Google GPU ISA or AMD ISA, you might not find it. Yeah, like, any progress? No. Yeah, so last stream we got the new version HCC in. That was good. We didn't make any progress in actually doing the occlusion stuff. But I have made, on the Discord, I've posted a new thing I want to do after occlusion. It's occlusion buffer. And I think this occlusion buffer isn't going to be something that we're going to actually go with in the end, but I want to finish it just to sort of see where it goes. I want to get some performance metrics, and I want to sort of, because if I didn't do this occlusion buffer, if I didn't do it, I wouldn't have found the problem in HCC and made HCC, like, add Intel support back again. I wouldn't have found these problems. And so I think it's good just to follow this through, because it only take one more stream, and I want to learn a whole bunch from it, basically. So yeah, we're just gonna test the first shader that we wrote, and we had to stop. So the clear we've just done. So that's not the first one. That's okay. I guess it is the first, but we wrote this one. Right, we wrote the occlusion pixels out. Sorry, we get an inner sphere bounds, or the inner axis line bounding box of a sphere. So this thing in screen space. So there's the nuclear plane getting into screen space, and then we write a single pixel out to the screen at the appropriate MIP level. So we're about to run this shader for the first time with this address, where we get the address of a texel and with atomic minute. So let's see how this goes. We'll see what sort of performance metrics we get. So occlusion, right. Okay, so what are we doing? We're dispatching over all spheres. Okay, so where's the spheres? Spheres counts. Yeah, it's pretty cool. Pretty happy about it. Like, yeah, this is our R&D, right? So we're going to take some routes which aren't quite what we're going to finish up with, but it's all good because we get to learn and then make better decisions. So yeah, it's going to be sweet. Like, so the next few streams will be basically preparing for doing lighting and shadows and thinking about all that good stuff. So let's see how. So we've already discovered that this clear shader isn't quite as fast as I would have hoped, because that's clearing the whole screen. Oh shoot! No. That's clearing. Yeah, that's clearing the whole screen. But we're clearing the whole screen using texture views, and it's actually slower than clearing something that hasn't got any MIP levels. So these have MIP levels, and because they have MIP levels, the clear ends up being slower. Or maybe it's not MIP levels, maybe it's something. I can't quite, but yeah, it's probably because it's got the MIPS. So we do a sync. Oh, no, it's not. It's not because it got MIP levels. We synchronize on the whole occlusion texture, and we go, so here's all the MIP levels, here's the whole texture, right? We synchronize on this, and we say, hey, by the way, it's going to be written to in the compute shader. And then we dispatch all of them at the same time. So basically, the reason why these look like they're very slow is because they're actually running all at the same time and using all of the compute units available. And they're all fighting for being. So effectively, this isn't a good measurement of how long. So it's not this plus that, plus that, plus that, plus that, plus that, and so on. It's basically, this is how long this shader has ran for, but it's overlapping with all the other ones in some degree. So this isn't actually a good metric. So what we should actually do before we carry on is have see this total number. I want to make sure this total number isn't adding all of them up. I just want to double check that. Yeah, it's not a plus equal. Exactly, it's not an accumulate. It's a... Yeah. It's not one of them. Just go into the GPU for a sec. We've got a performance thingy. See, a start and an end. And I think that's what we... Ooh. Yeah, that's what we're using as a start. I think so. So we've got an entry. It's got a bunch of entries, and we basically take entry 0 and entry last and take the difference. That's what we're doing. We must be doing that because there's another thing. Why the hell are we measuring this? Oh, it's in graphics, that's why. Yeah, there we go. So it's just taking the difference between the last one and the first one, and that's the total. So that's a really good way to do it. Past Henry was on point there. So yeah, we've got to be careful how we read these metrics, because if they overlap, then it's, yeah. So we should be looking at this number really. So let's disable it and see how much it really added. And that's the reason why it was noisy. Well, I'm not sure. Oh, but the clear will be running at the same time as these guys. That's why clear became noisy. Because these are all fighting for the same compute units and that. Right, got it. But it doesn't mean it's running slower overall, it just means that the timing information might look a bit wrong. Okay. So I disable that. How many ms are we dropping off the end? Total 10 milliseconds. What have we done? Why is this ray tracer just got slower? I ran the tile binning twice. So I just increased. Shoot. I copied the tile binning, right? And pasted it because I wanted to just change it. That's why. And I had to running it again. Right, so here we go. About 5 to 6 ms. And then we enable this. Right, so it adds like about 0.6 ms in total to do all of those clears. So if you add all those up, it seems like it's more than that, but it's not. That's good. Okay. So what do we want? Those numbers to be lower or just more stable or both? It's hard because that's telling us how long that shader specific shader runs. But what we should really do is say we should probably include the start and end times in the print information. Ugh, no, it's hard. I'm in the wrong one, that's why. Where's the Vulkans? Timestamp. Yeah, top of pipe, bottom of pipe. Yeah, it's all fine. Yeah, so those time a single dispatch. But if you put a barrier, so we've probably got like a barrier before this one, and probably got a barrier that comes after these guys, like just before the binning. So these can all run in parallel, ideally, right? They can overlap each other, and it doesn't matter. The GPU can schedule it however it likes. So the timing is going to be variable for when that individual shader actually finishes. So it's unclear what we want. Um, yeah, so I think if you're doing profiling, what you want is a barrier between everything, right? So if you're profiling a specific shader, you want a barrier implicitly to be placed between everything. That's what we should be doing for doing true profiling. Okay. So maybe we should look into doing that. Is there an easy way to do that? So we should have, because we can do it directly. No, we don't have to go into the backends. We can go into the front end GPU. So where it does the dispatch, we've got the thing that puts in the pipeline. Here, the resource barrier. So it's saying if it has any stuff to sync, so every time you say sync resource, welcome, I'm Kept Payne, how you doing? Yeah, I haven't got an RDNA 3 card, Socom, I've got an RDNA 2, even though I made my PC somewhere around then. I went for a year old hardware, because it's just cheaper and I don't really need the new shiny, you know? Right, so we've got sync resource. So what we should say is, so we should have a switch somewhere, basically. Just not the Nintendo Switch, just a Boolean switch, you know? Where we just basically say GPU sync between everything. And we'll have it as 0, yeah, switch at 1, that sort of thing. So this is what you switch on. So like enable this to see if we're getting profile results. Yeah, it's different. Or maybe it should be part of the profiling toggle it at runtime. Yeah, we'll toggle it at runtime. So when you have that profiler enable thing, you should be able to say profiler, profiler, so if you just have the profiler enabled, it's not really, you don't always want this behavior. You want to toggle it because you want to profile the whole frame. Let's have a profile mode. So we'll say GPU profile mode. And we'll say whole frame or individual shaders. So this you have a little mode that you start it on, and then what we can just do is you say is profiling. Right, so maybe you say like none, right, and then you just basically say set mode. That's what we'll call your new one. And then, so you can set a mode. Profile mode disabled. Put defaults on here. You set the mode. And then there's no longer like a start and stop. Like start and stop functions typically not a good idea anyway. So you want to profile mode. And then that will just be doing good, thanks. How's been your day? Yeah, it's not been bad. Just been to church and that's about it really. Been trying to get the baby to sleep. Basically my day so far. But yeah, weekend's been good though. Just been chilling. Did lots of working out yesterday. So yeah, feeling good, and that's about it. It's pretty groggy outside, so you know, stay indoors. Not that I'll go outside anyway, but yeah, that's just, yeah, just another excuse to stay indoors. Yeah. Also, just been thinking about how I want to do things next after this occlusion thing. So, yeah, been doing stuff like that. Pretty good. So we've got this new mode. And then, oh, okay, I wanted to go back. So, right. So we're just literally just going to profile mode equal profile mode. Not really rocket science. Yeah, let's just do all of that one. Delete the stop one. Ooh, what is this? Change the profile mode, might as well reset all of that, I guess. If the profile mode is equal to profile disabled, return false. Bam. So we can now set the mode, and the mode is going to be on individual shaders, right? So now every time we do a synchronized resource, which you do before shaders manually, and you go, oh, I'm going to write to this thing or read from that thing, we could probably automate that with HCC, but I haven't done it yet. Purely because it's not too crazy right now, but if it gets crazy, I guess we could do it. So this essentially just marks on each resource and say, oh, this one was written to, so then the next time you read or write to it, you have to put a barrier in between those two dispatches, right? So you don't have like any reads and writes overlapping across multiple threads, right? You want to put barriers in between to stop that. So it's just a very basic system to do that, and it's a lot easier with compute only, because that's all we have to track is read writes. That's basically it. So all we need to do is, so this bit of code says if it's like a texture view or an alias to something, right? We just get the resources aliasing and just synchronize on the whole thing. We don't care about individual MIP levels. We just sync on the whole texture, because doing it on the individual MIP level on array layer is actually quite complicated and a lot of work, and it puts restrictions on your code. So we just want to avoid that. And then this gets the sync state, and this sync state just basically keeps track of how it was used before and how it's going to be used. And that's the type of stuff you need in Vulkan, is you need to know how it's going to be used. So this is basically read write, that sort of stuff, right? You know, it's just, you know, read and write, you know. So this code here is going to say if it's writable or previously was a writable. We're then going to go into here, and then we would say make sure it's not overlapped. So we're going to have another Boolean, and we're just going to say, hey, is profile individual shaders And then we're just going to get that boolean. We're going to say GPU profile mode equal GPU profile mode individual shaders. And then we're simply just going to say or that guy as well. And then here, if it's not equal to, and that, yeah, it gets a bit confusing with all these nots and ands and that, but I'm just going to make it worse. There you go. Then we'll go into here, and we're basically going to push. We're gonna, yeah, this basically is a unique insert, right? A unique push. If it's in there, don't do anything, but if it's not in there, put it on the end of there. And we're basically going to say next time you do a dispatch, synchronize. So we're just going to synchronize every time. So we should be getting more, you know, some right, 2 seconds. We should be getting some proper legit profiling benchmarks now. So I don't know if we're actually putting a barrier in between everything. Looking at the numbers, I can say, I can't say for certain. So we're going to do a bit of debugging, and that is simply dig out the Vulkan code. So let's look for barrier. Wrong one, pipeline barrier. Good. So we're going to be like pipeline. Let's write barrier. And then we're going to do a dispatch. Let's write dispatch. We'll see how it goes. Right, clearly we're not putting a barrier between everything though. So, whoopsie. What have we done wrong? So doing individual shaders. I know why. Yeah, this is not the good place. This is not the place to do it. This is really not the place to do it. Yeah, so the problem is when we do the GP, so it is doing it. It's putting a barrier in between everything. I think. And why is it kind of multiple? Oh yeah, because that's probably the indirect. I'm not sure why we didn't do that. Wait, let's quickly find the dispatch. There's a dispatch indirect as well. So the reason why it's not doing it on all of them is because we don't call synchronize resource on all of them. So you go to, when we do the occlusion, clear, we just sync it outside the loop, and it is dispatch, dispatch, dispatch. Well, you didn't. If I call this inside here, then it would synchronize on all of them. But if I put it inside there, it's gonna, like, I don't want it synchronized on all of them because I know that, you know, these are gonna do each MIP level independently. Right. So when I'm not profiling, I don't want that behavior. So I'm just gonna sync on the whole resource and then do all of the individual MIPs. Hey, leave you. Dragnir. How's it going? How you been? So how are we going to solve that problem? Are we going to... I don't know if you could put a barrier down without anything. So this is where we need to look. VK command pipeline barrier 2. Now I'm thinking... I think that you don't need any. Can you get it to do a barrier regardless? It's not 0, then it must be a valid pointer. Excellent. So you can put just a standard pipeline barrier down. Yeah, because I want it to be a barrier. Because the rest of it is cache flushes, right? So the hope is... So this makes it them all go in there. Right, so maybe... Let's get rid of this quick. Yeah. So, I don't think we need that then. So the idea would be... On the dispatches... Dispatch... Or... Let me put that there. And if we do that for all of these barriers, will they happen? So even on this buffer 0? Yes. So we did it that way instead. Oh yeah, perfect. So we've got barrier dispatch, barrier dispatch, barrier dispatch, barrier dispatch. So hopefully that actually puts the... I don't know, they look like they're overlapping to me. Hmm... See, I wonder what happens if you put a barrier with no... Yeah, I'm not sure what happens if you put none in. I remember reading the documentation, it seems like it might have done it, but I don't know. Awesome, good to hear, man, good to hear. Um... So... Let's remove all these. Now look at the numbers. So we've got... They seem pretty still to me. They are moving a bit. Hmm... I still think the GPU could run it. It could look at the pipeline barrier and be like, nah. Let's quickly look into, wait a minute. Yeah, we definitely still want, yeah. Let's open up render doc and have a gander. So I think we should be able to see the command buffer from here. Uh-huh. You're not sure you can see your barriers. Yeah, you can see them. Yeah, it's got an empty barrier in the... Yeah, so it's clearing it. So it's doing its job, right? But also, the way it's dispatching is wrong. It's dispatching way too many threads. Can you see these numbers? They're the same for each MIP. Dispatching way too much. Let's quickly have a look at that. See, dispatching over the width divided by 8. Yes, that's the new width there. It's the dims, isn't it? We should take... Right, let's give that a launch. Right, that's way quicker for these ones at the bottom. Now I think. So should we change the profile mode and see what these numbers will look like? Well, no, we could actually put an explicit... We can actually change the explicit sync. We can make it an explicit sync. Let's move this inside here. And this will make it sync regardless. So let's see if the driver's optimizing that. So we're getting about 0.05 to about 0.15. Yeah, so put the sync between them all, and it's made these ones way smaller, right? Which tells me that that barrier is not working. Which is not good. Yeah, the barrier with no resources in it doesn't actually put a barrier down. So what we want to do is do this, and then use that no overlap one that we've got. So it's right only, no overlap. That's what we want. So let's try this one out. Yeah, I'm not sure why it jumps like that now. Huh. Yes, this is fine. This is what we expect, right? Because these are now... We've got a bunch of dispatches which are all being ran at the same time. Well, not at the same time. The GPU is allowed to overlap them across all of the compute units. And so they obviously will take... This is the time how long that one shader is running for, but obviously it's been paused and started again, paused and started again. But that's the length it starts and then stops for each of these. So if I then enable... So let's go and undo that thing we did in here. And let's put it back in here. So we decided to be like, no, let's just put an empty pipeline barrier out before every single dispatch or whatever else, right? This is a clear, but yeah, before every dispatch. If we're in profile mode individual shaders, but that didn't seem to work because an empty pipeline barrier seems to get optimized away by the driver, which makes sense, right? But I just didn't know that for sure. I think reading the spec, it was unclear what that would do. So now we're going to go back to this approach, where we're just going to make every time we sync, no matter what it is, we're going to make it create a pipeline barrier with all of the resources taken note of. So even if it is this special one, so we've got this new other one which is at no overlap. So if you see a series of dispatches with a bunch of no overlap resources, what's the way of saying it? So this dispatch, it needs to write to this texture. And what we're saying is that when we write into this texture, we'll promise you we're not going to overlap with any other dispatch. So if we say no overlap on this occlusion texture and we dispatch something, and then you do another one with no overlap and dispatch, you're going to promise you're not going to overlap. So it doesn't need a barrier. It only needs the barrier there once So you shouldn't need that there. All right. So if we run this, what were we expecting? Yeah, I think this is, okay, wait, what we got? Yeah, we've got the profile thing enabled, haven't we? Profile individual shaders, we've got that enabled, which means the timings we're getting are correct, right? We want there to be a barrier placed in between, and we're getting the actual timings now of how long this one takes. So it's putting a barrier before it, and it's going to specifically only run this across the compute units, and then it will put another barrier down, and when it's finished, it's going to then run the next one. So we're now getting proper timings that reflect how long the actual shaders take. So that's really cool. So let's just confirm this and change it to profile mode whole frame. And this is going to not put the barriers down in between. And you'll see we'll get different timings, which is fine. But this one will be quicker. This final one should be quicker. So it means we won't get any noisy results if our shaders just overlap other shaders. We'll now only get noisy results if our shader itself is noisy. Right, the spiky timeline. That's what I mean. If the timeline is spiky, then it's because the shader itself is spiky. Yeah, so now the clear is still a bit weird. I don't know why that clear is so spiky. It's not been spiky the previous streams. I'm not sure what's gone on. But that used to be 0.04. Something's changed. Yeah, these are all pretty consistent now, and we're seeing how long they take. So you can clearly tell this one is MIP 0 because it takes the longest. It's the most pixels. And now we go down here. There we go. Right, so I'm glad we fixed that. So we wouldn't have fixed that today if we didn't do this. Right, we were like, oh, we know occlusion. We know we probably won't be using an occlusion buffer. We wouldn't have fixed this problem. So this is good. Right, so let's carry on. So now the answer is probably a sum of this at minimum. How long it will take. Wait. It's not the best metric, but you could add all these up and say, oh, it takes this long. But theoretically, it could take shorter time because they could overlap and be done quicker because there's not a stall in between every single dispatch, right? Okay, so we cleared the occlusion texture. Now let's run the other shader that we wrote. Okay. So we're going to bring this one in and we're going to rewrite it. So this is a copy of the tile binning. We're going to bring in the other one, which is occlusion, sphere occlusion right. So this is just going to write out to the occlusion texture for each sphere. It's going to write 1 pixel at a different MIP level, depending on how big it is. So what do we need for this guy? So we need the spheres and the occlusion MIPS base ID. So we're going to read on that one, and we'll read write. No, we're going to read write overlapped. Get these in. Read write, read only on the spheres. So you need the occlusion base ID. Occlusion MIPS base ID. So yeah, this will, each of our texture views are one after the other. So we just get the base, and we want MIP 4, it's just base plus 4. And it gets us the right texture. Output dims, spheres count, all good. So all the bells and whistles. Now it's got dispatched correctly, so we're going to get the occlusion right shader. We're going to watch that one. Over all the spheres, yep. Let's just quickly get this push constants in there. Just all right. There we go. So now, before we run this, I quickly just want to double check the shader, because this could blow up the computer, and we don't like blowing up the computer. So right. So we get the sphere index. We get the camera properties, get the sphere, get the inner bounds of the sphere. Right, remember? This is the inner bounds, right? It's the inner bounding box. So it's all of the area which you know is absolutely covered, which the sphere absolutely covers. And then we get that on the screen, in screen space. And then we we essentially, if it's outside, we do nothing. We round it to the nearest pixel. We then locate, we get the size of it, or we get the smallest size, the smallest edge of width and height. We then calculate the emit level from that. That we need to write a single pixel. Right, so we're losing precision here, right? We're cutting off pixels, so we can only write a single pixel. So it's a rough estimate. Where's the dimensions? They're up there. That's fine. That's fine. Okay, so then we get our origin to sphere. Calculate the depth, the furthest depth. Turn it into an integer because we don't have atomics on floats. Calculate a coordinate at that MIP level just by dividing it by that MIP level. Get the occlusion texture at the MIP level by doing that base ID plus MIP, and then write atomic writing. Excellent. So, right, let's write the word sync so it saves the hard drive in that. So, yeah, if the stream crashes, it's because the code crashed my GPU. It's just standard GPU programming on the Linuxes for some reason. But yeah, let's see how it goes. Right. I don't see it showing up. I didn't hit compile. Rightio, it shows up. There it is. So it's actually not pretty quick, right? 0.0 whatever. So should we take a look at the render doc and see what sort of images we've got? So here's render doc. Such a wonderful application. So we're going to take a capture and we have to steal the MIP levels and see what this texture looks like. And then we're going to propagate the depth values between them. Oh, what is that? There's something off with these numbers, not gonna lie. We need to investigate that. 101. What? That should be illegal. There should not be many 111s if they're all running the same compute. If they're clearing, this should be clear, right? Yeah, occlusion clear. That's wrong. It's not good. But anyway, we'll look at that in a minute. Occlusion right. Tile binning. Perfect. So the occlusion right, it writes that to this texture. Undefined image, undefined image, undefined image. We could just keep zooming in for days. What's going on? Why you know worky? So we got different MIPs, right? You're meant to have been cleared, my friend. So let's go to the clearer. See, that one clears MIP 1. This one clears MIP 2. So that one clears it. When you go to MIP 2, bam, it's cleared. So something is fishy is going on. Yeah, I think the way I'm calculating the number of MIPs I need is off by 1. That's why. Because it's not a square texture or something. I thought I am running it with the validation layer, not gonna lie. I thought it's already enabled. So it should have catched that 101, shouldn't it? Should we try and make it obviously fail? If we go to image view create, for instance, or image create, so here we create texture. If we simply just say right, extent $z equals 0, that is illegal. Sorry, .depth. This should crash. Damn you. Right, 1, 1. Can't create texture with 0. Right, that's gonna crash. It's gonna take a minute because running address to line like 4 times apparently, or whatever it is, 6 times on a massive DLL takes ages. Yeah, this validation DLL is like huge. It's like 500 megabytes or something dumb like that. I was going to put it in the repo, and then I realized how crazy big it was, and I was like, nope, doing that. Yeah, so we've got it enabled. So I don't know why it's complaining. So it's a bit weird. Weird. Yes, we'll definitely look into why that is. Because we divide round up. Obviously it's on 0 already. So the next problem is we know we're clearing all the buggers, right? So we don't clear 10. Right, something's definitely fishy. Yeah, so I think you can do a 0 that it just doesn't launch it. It's just anyway. So so this is interesting, right? So it is correct we need this many MIPS to get down to 1 times 1. But the numbers are off. Or something. Hey there, oh my days, I've got to pronounce your name. I'm not elite enough. Yeah. My brain don't compute. But hey, welcome. How you doing? Yeah, so clearly we calculated the right number of MIPS, but when we do this dispatch, we are off by 1. So we've done, right, so that's the y-axis. Interesting. So the y-axis did the divide on the height, and it's like, oh, this went all the way down to 1. Or 0. It went all the way down to 0, so they needed your divide. Right, so you just want to say max U32. Oh, I got this. Max U32 times 2. 1, 1. Now we know this. We also know our shader's buggered. I think so. We also know if we do this division, especially on the y-axis. No, it's only if we're trying to count a number of things. But if we're calculating a coordinate, it's fine. Yeah, so the whole point goes down to 0. That's fine. Okay. I think we're onto it. So now we at least clear all of them. Let's just double check that. Renadoc is the bomb. Yeah, I remember reading the source code for Renadoc, and it seems like it's actually like tons of work to do something like this application. So hats off to the guy who wrote this. Like I did some patches basically. They're not any big patches. It was to make HCC work, and then obviously I didn't know how to fully do it because it's kind of complicated. And thankfully the guy over at who makes it was like, just finished it off for me. Like with literally the next 2 days, and I was like, wow, it's a quick turnaround, quicker than I'd turn around. To tell you that. So proper cool guy. So if we check out our texture, here's our boy, and there you go, the 1-1. Oh, it's not set yet. Oh, but it's set now. Bam. So that's good. So we're now at least clearing it all to basically max value, right? 4 billion. Unforgiven. Oh, so that means I am unforgiven for not remembering your name. Okay. Thank you. Has it been there? What have we been up to? Oh! Wait, what is that? Oh, sorry, that's our output for our render. Right, so we got it here. So what texture is this? 251. Right, so we go to this. So this was the one we've cleared, right? Undefined image. What crazy is going on? Is it because I did the pluses and it was like, no, it's wrong? But it should have been a crash then, if so. Maybe it was like. Let's think about it. It was last being written to, so it shouldn't need a barrier. Yes, here's the barrier. 251, perfect. It says barrier. So yeah, so we should have a barrier between it to say that, oh, it's previously written to and it's been written to again. So let's just have a look. Have a look. Have a look. Here's the image one. Oh, it was last being used as a compute shader. Access none, access none. USOBs. Right, so that's the problem. They're probably running at the same time. Huh? Yeah, we've got to investigate why that is. Why is it not saying? Because this was right, no overlap. Yeah, there's something a little bit fishy because we've done no overlap or something on the previous one. No overlap read only. So when you did it as a proper like read write, it should put a barrier in between these guys, but it's not picking it up right. So what we're gonna do is put in a nice core breakpoint, and we're gonna go in the debugger and find the bugger. All right. Just hop into the so let's hop into the sync resource and just follow through for a second. So we get the sync state. So let's pop out the sync state and see what it is. So we got a 6. Before we got a 6, and then we've got after we got 0 right now. Because how was it used before? So before it was used as, let's just go to gpu.h. So this is it, right? So what is a 6? What's this plus that? So it's right, and it's no overlap. Okay, does that make sense? So let's keep following it through. And what we discover is we should go into here, and we should be able to insert. So we insert into there. Excellent. Then after it's been used as, probably a 4, right? Or 3. Oh, 2, read write. Yeah, 2, read write. Yeah, okay, right. So we'll hop into the next one, dispatch, and this should be like, oh, I've got stuff to sync on, so it goes into here. Does the first one, this is not the texture, so we're going to skip round. And then this one will be the occlusion texture. So I'm curious on this function here then. What? Why is the mode 0? We just saw it was at 6. Looking forward to see your engine in action in a game. Like in every time you stream. Excellent. Not Jay Purse himself. That's fair play. Yeah, no, I never chat in other people's streams. I get too scared. I'm like, oh, you know. Yeah, it's just my social anxiety when I post in chat. Just I'm like, yeah. So I don't bother typically posting in chats. Plus, it's always like quite difficult to. You have to have a real good skill to talk to people while they live stream because one, there's a bit of a delay, and two, you've got to sort of like be able to articulate your thing with based on the knowledge of the person who's streaming and like, you know, like can you communicate to them in the most effective way in like 5 words and type it in time. So it's a real skill. So now I have a look at my sync state. It's like, oh, okay. It's because it's not getting it. It's getting it for the. I'm surprised this has worked at all then. It's getting the sync state for the texture view, but it's not getting the alias. It's not doing it for the aliased resource. So remember we said we've made some texture views. We should really be using if we use it on a texture view, always just syncs on the thing it's aliasing instead, and just syncs on the whole thing because we don't want to sync on individual MIP levels because it's just an absolute nightmare. So rocket science. I don't want to do rocket science. So if we do the dispatch. But yeah, I'm looking forward to this game as well. It's going to be amazing. Like I think it's going to take time. We're going to try quite a few different things out, right? But yeah, it's going to be a lot of fun. Hopefully make something kind of unique, but it's not too unique, and that people are going to be a bit confused by it. And hopefully I don't end up trying to make something that's too big and takes too long to develop. That's another thing as well. It's not my specialty. We've got to find something nice and simple. But it's not too simple where it's boring, you know. So there's that. Right, so we should be pushing on the resource. I didn't see any problem, right? So we're getting. This shouldn't be the alias. Because we go, oh yeah, get the alias and just you reassign that. So I don't see any issue. Right, so let's hop into the Vulkans. Resource barrier, aka pipeline barrier. In a Vulkan. It passes in an array of sync states. Holy moly, what is this? Have I been using the wrong sync states the whole time and it's just been working? So this is the array of sync states, right? You index with this with the resource. You literally index this with the resource index or the resource ID. The index part of the ID. Have I been indexing it with... Holy moly. I've been indexing it with like, with the, off the like, so we, oh my days. The wrong bloody index the whole time and it's just been working fine. What a bugger. We're going to delete this. This is done. Pass it in like that. It's misleading. I maybe had a different intention. Absolute scrub. How did I manage that? Man. I'm impressed that stayed up as long as it did. And you would have still had that problem in Rust. Just saying. Because it's just an array index. And it still would happen in Rust. Hey, Isaac. Oh wait. Is it one? Oh yes. Good old. Should have never worked at all bug. Oh yeah, definitely so. Definitely one of them. Yeah, the array was just big enough, but it just I'm just absolutely amazed that it still works because we should have been seeing crazy sync issues the whole time and they would have been unfixable. And in shader code, right? We'd have to fix them at this level. So confused. GPU dot ggpu dot okay, and then we do the whole. Let's just find the actual thing for it. This one. Give me the resource ID, and get me a resource index for it. Bob's your uncle. So the others all worked fine. Rightio. Let's run this guy. Oh, we got a crash. Oh no, it's the SIG trap. Because we got a programmable breakpoint in here. Let's get rid of that. Man, I love me some programmable breakpoints. Rightio. So, if we do a capture, we should be able to see it's possibly working. Well, I demo the engine to show what you can do so far. I like a demo scene with effects and so on. Grown up C6. Yeah. Yeah, possibly. I think when I have the style, maybe I could do something like that, but I don't know how much of a waste of time it might be. I think what might be cool is like when we can quickly create content in it and have like, well, I think after this we're doing lighting. Then after that, we probably want to just like Yeah, like I want to get to creating like essentially like a little model editor where we can essentially just make models out of spheres and then like animate them and stuff. And as soon as we can start placing objects down, it would and have an expansive scene that you could then just and like a lodding and stuff like that. That is probably at a point where you can do like a demo. Um, but until then, it's not really worth it. And hopefully I can get it running on Intel as well because we have Intel support now. But Intel is literally 10 times slower. So whatever numbers you're seeing here, times it by 10, that's it on Intel. It's really bad. It's like in some cases, like here 4.7 ms, times that by 10 people, it's like that's over your frame budget. So yeah, we've got to, obviously we're trying to make that go fast, this whole point occlusion thing that we're doing. But yeah, it's just, it'll probably be a good idea when I go a little bit further, I think. I tried to get excited about Rust, but I can't. Fair play. It's the thing is about Rust. I don't know how long ago it was now, but I did it. I used it back as 0.08, so about 1.34, and I can tell you that I was that excited Rust person who got a bit tingly about Rust. Had the giggles about Rust, but just want to spread the good word about Rust. But I never spread the good word about Rust because I was too shy to do it. But you know what I mean? You have that sort of, like all the Rust folk have. But eventually I just realized that it just got in the way of programming and I just went back to C anyway. Because I went from C to C++, then to Rust, and then went back to C again. But I spent 4 years in Rust. And then I ended up just using unsafe everywhere. And then just realizing it just got in the way. So, but there we go. It does really capture people in a weird way. Rust. Hey TJ Hooligan. What does this work you don't mind me asking? I basically do what we're doing now. I do 3D graphics. I'm a graphics developer. Yeah, I work at MM. Rendering guy. So I'm just honing up my skills right now. I'm just learning more and more stuff. But I'm also just making a game because I like making games, and I actually just like learning about whole stuff about making games and engines from scratch. So it's not just rendering I like doing, but right now we're doing rendering, so I'm just learning a whole bunch about rendering which I don't know about, and doing a deep dive into all that, sharing it all with you guys. Hey to the Hooligan, welcome. How you doing? Welcome. I like Rust, but yeah, if I was writing a kernel driver though, I'd choose it. Mr. Enums. Yeah, that's fair. That's fair. Yeah, I don't know. Safety thing is a bit. Yeah, it's there, and you can get it to not segfault, but at the end of the day, you've got to write unsafe code somewhere. And I guess you can isolate it, but you can isolate it in C as well. But yeah, it does do all that borrow checking stuff. So yeah, you are going to get it ensured that and you compile it. But yeah, I don't know. The part of the problem with Rust as well is like when you write something wrong in Rust architecturally because of the borrow checker, you have to actually re-engineer your whole thing, and you might be in the middle of prototyping. So I guess then you should whack into unsafe and just continue prototyping. But if you don't want to do any unsafe code, you got to then refactor your whole thing just because, like, the borrow checker's not satisfied with how things are. And I think that got better over the years with the way they did their system in the compiler, but it's obviously still a problem because it's a restriction. It's got a restriction. Right, I see things. So this is the compute, the occlusion. Right, okay, perfect. So we're not seeing anything. We should be seeing lighter values. Oh, no, 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 no. It's perfectly fine. Yes. See, these are the numbers here. That's the maximum number. Basically, if I hover over it, it goes way lower. Which means, bum, 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 the view, the way it's being viewed. So RenderDoc is probably not the best application to do this in. But let's see if we can put like a big number. Perfect. There we go. There's the occlusion buffer, people. So I don't know what. I don't know why. All right, here's the MIP levels. Okay, so MIP level 3 is getting written a lot to it. So black, what does black mean? So obviously we've all got it in one place. We should probably have some of them move a little bit further backward. But black, yeah, it's kind of still a big value. This is not a good sort of yeah, it's not really a good way to view it. Yeah, we should really divide it by 1,000. We could write one of those custom shader things here, but yeah. But anyway, we're seeing in RenderDoc that it's showing good value, so we can actually debug that better by literally just viewing it in our game. So we'll just get that. Yeah, we can look into that. All right, 2 seconds. I just need to go and yeah, I'll be back. 2 seconds. Enjoy the little tunes. All right, welcome back, everybody. Hey, Crimson Mania. Welcome, welcome. Just RC, refs LT everywhere. You have to worry about the bar check. Yeah, exactly. Runtime bar checking is the answer. Yeah. And if you want it to work across threads, arc. Yeah. Let's go. Okay, so let's debug this now. So in the ray tracer, we're going to add another texture. And this texture is going to be this occlusion MIP, just so we can debug it. Yeah, so we'll just whack that in there, and then we'll have a way to literally just be like, oh, visualize this thing in the shader, and kabam. So just do a define up here. No. Occlusion, show occlusion, texture. So 0, also put it at 1, and then we'll say occlusion texture MIP, and then we're going to show MIP 3 because MIP 3 had it basically all on. So we've written a single pixel at a certain MIP level, and we obviously got to propagate them throughout the MIP chain, which is the next steps. But I just want to visualize it nicely so we can actually see how well it actually looks. And we can change that number. So if we go to the sphere ray tracer, this is it here. So this dispatches over every single pixel, so we can translate that pixel into a MIP thing into a MIP level quite easy. So we literally just want to find where we do the other things. I also almost tried to do the sorting thing, which didn't finish. Where are you? These are the spheres. Let's just take one of these. This just shows the outer bounding box and the inner bounding box. Let's put one here. So this one is going to be, it's going to say, right, if we put it against this thing, show texture. Now we're just going to take the U chord, the unsigned 32 coordinate. Next gets our pixel. That's our pixel coordinate. And what we're going to do is be like, sample that texture please at this MIP. So you want to get your coordinate. So I guess we'll just say X. And our X is going to be U coord dot X shifted right by the MIP level. And so that is the one we're going to select and sample and display on the screen for this pixel. Then we're simply just going to do a load texture. All right. So we'll get the pixel. It's a U32. P we'll call it depth U. What's this called? Let's do depth U. So that'd be load texture. It's not. I can't do my thing. Load texture G because I'm being lazy. So we're loading from a texture, and what we're going to use BC occlusion MIP's base ID plus this MIP. Then the coordinate we're going to load from is XY. I think that's all you need. Then we get our depth value as a floating point. So the way I've done it is I've just times it by 1,000. There's like a little scale. That's how I convert it from a float to an integer. I don't know how good of an idea that is, because you don't have atomic mins for floats. But I think you can just convert you can reinterpret your int as a float and do a min that way, but I'm not quite sure. I need to double check that. So for now it's times it by 1,000. But it doesn't matter because it's just test code. It's obviously made it harder to debug in RenderDoc though, so it kind of does matter. Right, so next thing we're going to do is basically just visualize that depth by just storing it in the output texture. So let's do the flip. So we splat that out into so you go depth, depth, depth. And then you say 1 for the alpha. Bearing in mind you kind of want to divide it by the max depth. So I guess you just call it R, be depth divided by, what's the max depth? I don't know, let's say 500. Well, let's say 256 because then you actually get a map into a, yeah, so just say R. Right, and then you got your flip upside down, do the BGR conversion, because we have to do that manually now. Which ain't that bad. And then we put it out into the final image. Right, so I need to make sure that we quickly put that into the sphere ray tracer for some debugging. Just a read only. And then I want to also synchronize on it as well. think it runs into any problems there. Alright. Misho, little guy who runs around on his island with it every time. Oh, yeah, that old thing. Yes, I remember. Yeah. Mhm. Yeah, I remember the might be right back before I had the new logo, where it was that pixel art game that I was trying to make type of thing. Long time ago. I remember the reference now. Yeah, lots of little projects I've gone through. Yeah, made a little editor for that. You could place stuff down and stuff. It's pretty cool. Right, so we should be seeing something, and we're not. Oh, we didn't enable it. That's why. Derp. Right. Oh, I need to get the texture. I love bindless, man. Bindless for the win. Yeah, technically that's invalid C, right? My compiler does invalid C there. It doesn't allow you to compile depth equals depth divided by that. But that's actually valid C. I just haven't handled that properly. But it's not error prone like C is because of that. Sorry for the blind and white screen, guys. Apologies. Seriously, why is it? Is that because it's too high of a number? Should we do 64? Right. Please put the sunglasses on. Right, it's not. Let's do 8. Is it negative? Ugh. Oh, we're grabbing MIP 3. Oh yeah, we didn't know exactly what MIP... Well, no, I saw it as 3. Right. We could be grabbing one which is fully on, basically. You know what I mean? Let's have a look. Let's give it a launch. Guess the capture. So I want to find the right MIP level where we're right into those values. Um, this one. So that ain't it, because that number's not changing down there. It is 3, it's MIP 3. And MIP 2. Yeah, can you see it? You sort of send the balls there. That one's not really checked, but yeah, so 2 and 3 have something. So we should be seeing stuff. What is going on? Hey, grandson. Make an updated version of your engine. This time walk around with your wife and kid, zoom in and do the Ta-da, dance. Yeah, I gotta make us all in the new 3D game. A lot more work. Yeah, cool. Speaking of C and HTC syntax, I saw you did a BGR swizzle last stream. Did you implement that CPU as well? No, it's purely compiler. So I added swizzling as an extension. Yeah, it's purely GPU. I added it swizzling as an extension to my compiler, and it works for as a L value and R value. So it's pretty sweet, and it also optimizes it. So if you do like a chaining of swizzles, it will narrow that down to just one swizzle. Um, yeah, it's quite fun actually. It's quite easy to do that. Yeah, so we have so if it's pure GPU code, I just swizzle because it's just easier. Like and I also support like doing stuff like that. But if I share it between CPU and GPU, I'll do it manually. Yeah, they should. Yeah, because kind of it is a nice feature when you do shaders and stuff. Yeah, it's pretty sweet. But yeah, how's it going, Cranston? How you been? Um, so why oh why do you not work? What is a wrong with a you? What is a wrong? You say MIP level 3. Yeah, shift right. The coordinate by MIP. Load it. Divide it by the scale because you times it by the scale to set it in there, right? Depth U. What sort of depths are we dealing with? Could I go to the shader? Oh, there are like 1,000, are they? That's why. There are like 1,000. Yeah, I'm not sure that's going to map easy to. Alright. That's why. So they did like wait, what size are they at? I turn yeah, so about 1,000. Let's do 1,200. Or 1,500. You'll see something. Yeah, so it's divided by 1,500. That's why. Excellent. Excellent. So this is the MIP. So we're seeing the depth, right? So the more white it is, the further away it is because it's higher the valley. The more black it is, the closer it is, right? So what we're clearly seeing. Wait a minute. So imagine this is the far plane. So if it's white, then it's probably not got anything there. But if it's like black, then it's definitely got something there. Yeah, that's a good way to say it. So if it's white, it's not got anything there. If it's kind of black, then the gray's black, then yeah, it's got a pixel there. It's definitely occluded at that pixel by some sphere. So see these are dancing in and out here. If we go to the other MIP level 2, so this is the one that's higher resolution. And we're only writing a single pixel per sphere, by the way. Here they are, right? So there's all the black ones, so where there been a single pixel is being written for a sphere. So what we need to do is we need to get these depth values and combine them all together. So you won't be seeing any of these ones dancing around because, or as much. And you on most of these gaps, see this, it's all white here. Well, it's definitely been occluded here, right? We're definitely occluding, there's definitely spheres being occluded here, but they're probably in a different MIP level. So you should see them. You should see a lot of this white disappear, basically. So there's still the spheres, right? The axis line bounding box filled with spheres. They're still here. You can see them, right? But we should be seeing less of this white. So we need to like join all these MIPs together now, because we're only writing one MIP for each sphere. Each one of these spheres is writing one pixel on one MIP level. So it's kind of like a rough guess, but it's meant to be really quick. And it is kind of quick. It's 0.02 to about 0.4 or 0 point something. Yeah, about 0.1 ms. It's actually quite quick. So now we've got to write some propagate shaders, which propagate all the depths. There's an extension for vector subsequent GCC. You can use it. Yes, you can. That's pretty good. Yeah, so the only thing is you have to be careful with those is because those are actually aligned to 16 bytes. So if you're doing scalar alignment, you have to make sure you do that attribute. You have to make it align differently. Yeah, so you have to. And I did test it; it is possible, but I decided. I think I've put them in the. I think I put them in my HMaths library, or I might remove them. Let's have a look. Third party libhmaths, HCC libhmaths, types. Yeah, I removed it. I forgot why. I forgot the reason why I ended up removing it. But yeah, you just gotta be careful. Those things are aligned to like 16 bytes, so they load directly into a SIMD register and that. Right, so we're gonna write a new shader. This one is going to be the occlusion propagate forward or backwards, what we're going to call it. So let's write these ones. They're going to be super easy to write. Let's go to the Discord. And let's go to the notes. So basically you got your MIP levels right, and each one of these have the depth values. But you might have written a pixel here which has been like 33, at a depth of 33, and technically this thing should span all of here, and you've written a pixel here of 77, and 77 is obviously greater than 33, but if you were to read a single pixel to see where a sphere was at, to check if it's occluded or not, you wouldn't get the 33 values. You need to propagate this 33 all the way down to all the pixels. So next time the sphere that wrote this 77 reads that same pixel, it's like, oh, there's actually something that's blocking me. I don't have to render, right? So that's what we need to do, the propagate. So this should be pretty quick because it's not using any atomics. So here's the code. Here's the plan. So dispatch n-1 MIPS to propagate back from the higher to low MIPS. So back propagate, the depth values do min, and then forward propagate. Yeah. So propagate backwards propagate. You just need propagate, I think. Propagate one. Yeah, you don't need any. Yeah, we'll just share that. So how we're going to do this is probably by. So you get 8 by. You're probably doing 8 by 4 because that's 32. Do an 8 by 4. Take all those values. Do a min. Oh, that's my other one. My future notes for the next thing we're doing in the next stream. Okay, so you want to get your source texture, destination texture type of thing. So you want to get. So we're reading from. Yeah, so we'll get the one. We'll say something like. Read write texture. Oh, we didn't need that. Right, so an 8 by 4. So you want to essentially load 8 values. So you're propagating backwards, right? Which means you propagate from the low MIPS to the high MIPS. So the low MIPS, or the high MIPS to the low MIPS. So the higher ones will have one value that you get. So you get your depth value. Maybe just keep it as E32. Depth U. So your load texture. And you're going to do a load texture for BC. Okay, I need to do this one, basically. Or whatever the MIP level is. So the MIP level will be passed into there. And then now we're passing in the specific. I don't need to know about a MIP level, do I? Yes, this 8 by 4 would probably be the destination. And you need to read from one source. So you'll get your source coordinate, and that would be essentially whatever the SV dispatch index dot x shift right 1, right, just divide by 2. So that's your source coordinate, and your destination, you've got a base destination coordinate, and that is this one. Oh no, sorry, it's not. You don't worry about base. Oh wait, I'm reading this wrong. Right, so it's 8. Yeah, each thread would do a pixel. They're all going to be loading the same. Yeah. Right, let's just do the easy code. Yeah, so source coord, destination coordinate. All of them will just load. They'll be loading from source, occlusion, texture, and you'll be loading with source coordinate. So that's the depth value, and then you'll basically just store. I think you'll do a load, source depth, destination coordinate. Yep. And then you'll basically do a max as your new depth. That'll just be a... Wait, what are you going to do? You want to get the... You want to min them. Yeah, because you want to find the closest depth and then write that back out. So each thread gets its own pixel, but they will probably read the same source pixel. Right, so what's the other ones? You say propagate forward, low to high. Max of 2 by 2. I'm not sure if that's what we want to do. Yeah, no, we might have to do something like that. Okay, and then we're just going to store it back into destination. Store. Hey JV, or JV maybe. Hey, how's it going? How's it going? Depth U. So that should be propagate backwards. You're going to propagate forward. So that's going to go from the low to high MIPS, read a depth, find the minimum between those, and then the minimum between the current pixel we're writing to and the one that we've just read from, and then store it back out to just, you know, the one we're meant to be writing to. And the source one obviously comes from the lower MIP, which is half the texture size, right? So now we're going to do another one, which is propagate forwards. And this one is going to work the other way around, where the source is this one, right? And the destination is one lower. So you're going to be reading one pixel. So this is where I don't do, or do you read a 2 by 2? You should really be reading a 2 by 2, and then yeah. See, this is where I think we should be doing. You should be reading a 2 by 2 at source coordinate, finding the maximum out of those and then minning it. Something like that. So you would do like a... So your source coordinate would probably be destination coordinate. No. I had that all wrong. Destination coordinate is probably that, and your source coordinate is probably the same thing actually. Base source coordinate. Oh, it's times by 2 in it. So you'll read 4 pixels. So it'll be 30 times 2 dot x plus 0, y plus 0. Repeat that 4 times. 3. So you'll go 1, 1, 1, 1. Right, so you just get the 4 in the quad. You find a maximum of those 4. So you just do source depth you... So the reason why you put the maximum is because you're taking 4 pixels in a quad, and obviously if you've got 4 pixels, let's draw this out a bit. Half is 1/4. Yeah, that's probably just definitely think about that wrong. So you've got like your source is when you're propagating forward, so you're going from the high resolution to the low resolution. Is that right? From the low MIPS to the high MIPS. Yeah. Falling backwards is maybe, I don't know, could be relatively either way. But anyway, from the high resolution to the low resolution, you're taking a 2x2, you're sampling, or you're loading these in, you're finding the maximum between those depth values, and then you're going to output into the single pixel into the higher MIP. And the reason why you take the maximum of these two and then min it with this one is because these 4 pixels alone, or this pixel here is meant to represent what is the sort of minimum occlusion where I can guarantee that there's nothing else behind me. So you basically have to find the furthest distance between these guys, and that's the thing we can guarantee. So if one of these, if these actually hit a sphere and this one hit the background, then unfortunately you got to put the minute with the background here. So they all have to be occluded by a sphere or something for that to work, but that's fine. So you max U32 between all these buggers. Do that. Then you min that, and then you write it out into destination coordinate. Right, so that should be it. We just got to get the dispatches right, is all. Yeah, we could get this one to do a 4 by layer 4 hexaread the other way around on the destination. It might be, I think it's better if we do that for consistency's sake. So maybe we should do that. So if we rewrite it, where, so I think, so you're going backwards, you're saying, so the source, so it's base destination, and the source is then divided by 2. Then where this all says source, it should all be saying, and also this should be saying base. Whoops. Kind of effed that one up. Whoopsie. Right, so let's get these boys. Plop them in here. So we're replacing source with destination. And then this one is saying, yeah, find the max of... Is that right? Source. And then you're writing out into destination. Right, so let's read that. Make sure it makes sense. So to go backwards, you got your destination coordinate, we're writing to. Your source is going to be divided by 2 because it's the MIP level, the higher MIP level, right? So which is a low resolution. Then you look at the 4 destination pixels. So something's sketchy with this, but anyway, let's just carry on and read it. So you got the 4 destination pixels. Then you're taking the maximum of. No, so if you're propagating, it's just a min. No, you should be storing out. No, 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 no. We're not joining them together. It's the complete opposite. We should be doing one source load. One source load. And then doing a multi-source. A destination load. And then you basically store them back in. Depth. Something like that. Then that'll be. What one do you want to do? Yeah, then I think you want to do a. Equals a min between the source and that one. Then chuck it back out. So we'll do this as the DST coord. Boom. So say E32 times 2 DST coordinate. Yeah, I don't know how much better it is to do it this way, not gonna lie. Hmm. Yeah, I don't think this is the way to do it, because you'll won't happen on the last texture. Put that back. Like there. Right. So just got to sort out these propagate push constants, and then we should be able to give that a spin. Hmm. Yeah. It wasn't the way to go, I think. Um. Yeah, so this should. Yeah, problem with running it is you don't want to crash the GPU. So I just want to double check it. There's no dash G's in Shader World. You have to be the G yourself, unfortunately. Right, so occlusion propagate. What do we want to have in there again? So we wanted to have the a destination and source occlusion textures. That's basically, isn't it? Yeah. So you're in your occlusion texture. Read write. Source. Okay, read only, destination. Destination. Perfect. Right, so let's just quickly double check this stuff. So if you're going from you're taking a source from the MIP before you, so we need to be targeting. This is one at the low resolution, so this would target a 1x1 just fine. And getting all the way up to the highs. The higher resolutions. Yeah. So you get your current pixel, you're from the current pixel and the one before you. Min those. Yeah, I think I could have written it the other way actually, but this is probably just better, it's more simple. Now this other one is going from the high resolution to the low resolution, and it's propagating that. So it gets the quad of pixels So destination, it gets the quad of pixels it's sampling from, finds the maximum between those, mins it with the destination one, and then writes it back out to the destination. Right, that should be it. So we compile it. Should be working. Oh shoot, I changed the wrong one. The tile binning. Shader got bugged. There we go. Oh, you got it. Excellent. Thank you. Appreciate it. Right, so now we should go into the graphics. And we should be able to say occlusion. Where is it? Occlusion clear, occlusion right. So we got to do another for loop. So we're going from, so it's from 0. Yeah, so we're going to do n number of MIPS minus 1. This time you want to do a read-write dependency on the whole thing, every time. So these will block every time. Propagate. So you got source texture, destination, source. So what are you doing exactly? So when you're doing the backwards, you're going from the lowest resolution up to the highest resolution. So it's basically like take this, take 1, and then it's take that, take 2. Wait, which one is take 2? So your destination is take 2, and your source is take 1. So that'll get you the back MIP. So this will get you the back MIP, this will get you the one before the back, and so on until you reach the highest resolution. And then you dispatch it on propagate backwards. And you're dispatching, so you got to be careful here. You're dispatching across the whole, the resolution of destination. So the resolution of destination is, there's not really MIP level anymore. Let's call it index. So we'll just say like destination MIP level. Let me do this. Oh, did I do that the wrong way around? Shoot. Anyway, we'll redo it. So destination MIP level. Source MIP level. Right, let's try this out. So source is the one from the back. Yeah, destination is one for a bit further. Good. So this is the what you want to apply to get the dims. So it's destination MIP level. And so we can use that resolution to decide how much we're launching, and it's 8 by 4. So if I run up there, it's got sort this one. This is propagate. Excellent. So that should be propagating backwards, and then we need to propagate forwards. It's a little bit different, so we've got to be careful. So destination is, so it's forwards, right? So it's just index. So destination is index plus 1, and then source is index. Now we're going to get the resolution. So your destination, is that the resolution we want to use? Yeah, it's destination. Yeah, destination is the one we want to use. So it's the same thing. Destination MIP level is the one we want to dispatch on. Cool. So this is propagate forward. Gotta be careful there. And where's the sync? Yeah, the sync code's here, which is good. Let's move it down. Rightio. Let's give this a spin. Hopefully it doesn't crash my machine. If it crashes the stream, guys, I'll be right back, but hopefully it shouldn't. Everything looks legit. Let's double check. I've got those two sync. Yeah, so let's give it a go. Alright. It's happening. So we've got loads more dispatches now. This is part of the issue with it, is it's just going to give us tons of dispatches, which is probably not... It's probably fine. But yeah. So there's one of them which takes a lot longer. That's obviously the highest resolution. So going backwards, right? Low res, low res, low res. So that's one pixel. That's 2 by 2, 4 by 4, 8 by 8, 16 by 16, and so on. Well, kind of like that. And yeah, so we go all the way up to our native resolution. And as you can tell, when it gets to that one, it gets, it actually starts to take some form of time. Now this one goes from the high resolution down to the low resolution, right? So as you can tell, it starts off at the most and then goes down. So overall, that's really not a lot of time, I would say. But yeah, we should have built up our occlusion buffer now. So should we see the final result? So what we can see is we should be able to see in here, if we enable the debugging, now we should see a lot less white lines in the middle of the screen. So if we run it, oh, this ain't good. It's fully black. I'm not expecting to see fully black. Map 2. Hey, it's Prestoni. How's it going? Yeah, man, ask away. Yeah, so we shouldn't be seeing a bunch of black there. Like, that just means we're getting a bunch of zeros. Been written in. That's not sensible. Propagate backwards from the low resolution to the high resolution. Should we disable? I think it comes from the fact when you propagate backwards. So what we can do is we can actually disable propagate backwards and see if that's the one that's causing it. And if that's the one that's causing it, then we should have to investigate that. Now to make logos, I need one from YouTube channel on music. Aha, as I expected. I'm not sure if I can help you with that, really. Sorry. But yeah, it's just, you can always contact someone who makes logos, or I just make my own. Yeah, just use AI. Yeah. Just use AI. But yeah, that's got questionable, if you're small, it's probably fine. You probably get away with it. But if you're big, it's probably not the best idea to do that. Right, so if we go out of bounds, this is where we've got to be careful. So you're going backwards. So if destination goes out of bounds, 8 by 4. Yeah, I think this is part of the problem. I'm not sure though. We're running out of bounds on the textures. It's probably overrunning the memory. Sorry, what is this? This ain't what I'm looking for. Yeah, so if the coordinate goes out of bounds, that's what we're missing is output dims. So what are we exactly looking for? And is it destination again? If the destination one goes out of bounds. Yeah, because you only write into one coordinate. Yes. So you want to get your sort of destination E30 times 2 destination dims. Sweet. DST dims. So you get your DST. So you've got to make sure. So you're going to do that like right away, really. Move that down there like that. There you go. Right. So we need to fill in the destination dims from CPU side. So luckily we've already got them here. Okay. So it's got to fill in that as DST dims. And then away we go. Alright, so we run that. That should hopefully prevent some of the black pixels showing up. No, it doesn't. Right, so it's definitely safer though. Although we're getting a problem on the back propagate. So we're going from the 1x1s, and I think we're bringing back like a black pixel for some reason, and I don't know why. Why are we bringing back a black pixel? Your source is at the back. And let's just read the shader. Because if we disable this, we don't get the black pixel, right? If we disable this, propagate backwards, well, the black pixel is, you know, all of this was black here on this side, which is really bad. So why was we getting that, you see? Did it even compile? Okay, let's give it a go. Oh, I see. Yeah, it doesn't work. Right. So back propagate. So we're getting the the destination is out of bounds or bail. Get the destination depth, source coordinate, which is divided by 2. Read that pixel. Do a min. And then write the min back out. So why are you getting a black read? So we should open up in render doc, right? Even when this one's open up in render doc, because we should be seeing. So we shouldn't be seeing absolute black value on the high MIPS. There might be a tuning sweet spot and accumulating more pixels per dispatch, having fewer dispatches. Oh, you might need to do 1.02 dispatches. Yeah, so it might be quite negligible. But yeah, maybe, it depends. For the last one, it might be beneficial. Yeah, very true. Right, which one is it? So it's probably that one. So that's when you're building the MIPS. Building the MIPS. So you need to put like, big number. That's too much. Right, there we go. So the problem is like times by 1,000, so it's not going to be clear cut. So if you get up to the higher MIPS, we shouldn't be seeing anything written. They're all going to be like all on. Because as far as the E32, but I times it by... So the 1x1 is just that. 2x2. Well, it's not 2x2, it's 1x2, but yeah. They're all on. They're all on. They're all on. Getting a bit harder to tell now, but they're all on. So the back propagate. So we should be propagating. So propagate from 3. I don't know. Infinity. Oh no. Seven. That was enough. Wake work. Let's go to MIP 3. Yeah. So nothing's in the higher MIPS apparently. But then as soon as if we do back propagate, from those higher MIPS, right, let's double check all of this and we'll see if we'll find it. Let's take a drink. What kind of game we're making? Not sure yet. We're just building the base foundation of a game engine. So essentially just all the core things like, we've got keyboard, mouse, we can interact with the GPU, we've got a UI. So we're just building that base foundation we can prototype and come up with some graphics art style, which is hopefully unique, or not anything is fully unique, right? But just quite uncommon. So engine without game, that's exactly it right now. For now, it's going to be that way. Yeah, that's kind of where it's at right now, isn't it? But yeah, and then after that, we'll switch gears and make game without engine. So yeah, that's basically. It's funny how things have ended up this way. But yeah, but basically what I mean by game without engine is that you're writing an engine specifically for a game, in a sense. But yeah, we probably still generalize in some places where we don't need to, but anyway. There we go. Software development. So So destination MIP is 2 from the back, 1 from back, loop from back, in a sense. Back to front. Destination text, just check that. Read write, read only, yep. Synchronize on the whole texture. Destination is obviously that divided destination, yep. 8x4, good. That looks good to me. But I thought we read over this and I was like, yes, fine, but whatever. So in your destination pixel, where you're going from the one of the higher resolution, you're reading that one out. Then you get the lower resolution, which is divided by 2. Then you're reading that one out. Take the minimum between those. And then store back out the new depth. What? That should be fine. So why are you getting a black pixel? Like, so you're going from... So I guess we can see it in render doc. We'll be able to see each of these. So we can see when it happens. So let's run it again. Render doc is amazing. It's like one of the best tools. You can obviously build one of these in your game, but it's so much work. Right. So that's where you put them into all the spheres into the MIPS. This is when you start doing the back propagate. So here's the 2 textures. Both as outputs. Okay, well I guess there's no difference. But yeah, they're both. Alright, that'll be enough, I think. So MIP 1 by 1 and 2 by 2. We're not seeing any difference here. So we go from 2 by 2, 5 by 3. We start seeing black now. Ooh, look at that. So why is that happening? Why are we seeing on that 5 by 3? Why are we getting 0 appear? So you get coordinate 4. You'll go, oh yeah, divide you by... Oh my days. So that's a 5 and the lower one's a 2. So you got to check if you're out of bounds on source as well. Basically. But you do a 4, right? Coordinate 4. Yeah, divide by 2 days. So when you're propagating, what would you do in this situation? Should we just make it... Should we make the base a power of 2? In this case, to avoid this problem, just make... Because you're going to get, if it's not power of 2, you'll get an odd at some point, right? So if you have an odd, and you divide that by 2, that'd be 2.5. Obviously. Then it truncates. Yeah, we've not designed the algorithm for taking in an odd into account, I don't think. Is that right? No expects. Um, hmm. Can you do hardware UV clamping when you're min-maxing the same value twice? Should be harmless. Yeah, maybe that's the way we solve it. That probably makes sense, doesn't it? So you want to, if you've got this pixel 4, this big one over here, this big pixel or texel, you want to be grabbing this far right thing here, right? And putting that one there. But it'd be the same one here, here, and here. Is that fine though? Yeah, because that's half of... See, I'm wondering if I do the division. You'll never be able to write. See, I'm wondering about this shader now. When you're shifting right by enough of these, no, it'll write to the right place. Yeah, it should be. Yes, the problem is that the back propagate is you basically need to clamp it to it or something. Is that right? Yeah, because if you were to make it a power of 2 texture and just do the division, you'll pick like a pixel which has been initialized to the clear value, which would then mean if you read the same value, it should be fine. So we probably need the source dimensions in as well. Yeah, that's a good way to think about it. Let's do that as well. So if we go to the shaders, source, yeah, so if we go out of bounds on the source, so you just want to do a sort of a clamp S, no, it's just clamp E32 times 2 with BC source dims take 1. It's already sort of a minute, isn't it? Max source coordinate is sub S. Well, let's just pass it in as that. Just save it. Much better that way. Just take away 1. Right, so now in the shader, we'll just do that sort of like min E32 times 2. When you're reading that source. So when you're going to forward propagate, will you encounter the same problem? So your destination is a 5 by 3 or whatever it was, and your one below was 2 by 1. Oh yeah, it's a 5 by 2, 5 by 4, like a 2 by 1 or something. So on the x coordinate, you're going. Wait a minute. So you're going from the high resolution to the low resolution. And your source is that times 2. So you'll go from a. Which means you'll miss the edge of the. Wait, is that right? You would do a 2. You'll be a 1, wouldn't it? You times 1 by 2. Is that right? Yeah, she'll get 2 and 3, but you'll miss out on 4, which would be the 5th pixel, wouldn't you? So you'll just flat out miss that one. But you should miss that anyway, I think. So if that's the case, we should probably make, yeah, because you'd want to make sure that the, but then you'll be writing to the same depth pixel in different shaders. Yeah, let's just ignore it for now. It's not the most efficient, but it's safe. Because otherwise you'll be writing different threads, will be writing the same pixel, and that's not what we want. Right, let's run that. Okay, that's fixed it. So we're still seeing stuff. Some white here. I wasn't expecting to see white. But we should be seeing them propagate throughout the whole valley, the whole chain though. So we relaunch that, we get to verify it. Right, so it's done a couple of captures. So we should be able to see the full texture, occlusion texture. A lot of dispatches. So here's the last one, right? And we're not seeing much. I was at least expecting to see it in the highest resolution. Oh no, sorry. I forgot to do this in it. Yeah, this isn't a good debugging view, to be fair. Right, so we've seen it in the lowest one, lowest resolution. It's propagated all the way. Oh, sorry, highest resolution. It's propagated all the way down. So yeah, so the 2 has got some bits on it. It's got some things on it, but as you see, it's joined 3 into there, right? And then 1's basically got nothing else to offer, and 0, like the highest resolution. The spheres weren't a pixel big, so it didn't just write it into there. It just wrote a single pixel into the higher MIPS, and it's propagated down. So then you up to the higher resolution. Very nice. It's propagated there, propagated there. So when it's red, it's obviously says it's the background. So you're obviously not going to, if something's really big, it's not going to, yeah, it's just not going to see it. But yeah. Where this will work the best is if you have something massive, it will probably write into the low MIPS, right? It will write like a single pixel value, and that will propagate all the way down. So you can probably have probably put something in and see that, but then it will like basically overlap all of these, and then when the sphere reads back here, it will discard it. Yeah, so we should be able to plug that back in. I'll plug that in pretty easily, really, and just we'll see this number drop for Why is this sphere ray tracer so quick? What have I done? Oh no, that's because I'm doing the debug visualization of it, isn't it? Yeah, so as you can tell, we dropped down to 2. It'd be a bit more resolution. Yeah, as you can tell, it's got some like big pixels. If I zoom in, it's got some small pixels and big pixels. Where you see the big pixels, these are the ones where it's been propagated from the higher MIP down to the lower MIP, right? And so it's able to guarantee that these are definitely occluded. Yeah, so if they're fully white, it means they're not occluded. Like nothing's occluding that pixel. Like we can't guarantee anything's occluding that pixel. If it's gray or black, it means that something is definitely occluding it at this depth. So if you were to read the pixel there for that sphere, you'll be able to see if your sphere is being occluded or not. So we should be able to cut out a lot of. So let's go to the drawings. So the way we've basically got it set up is we've got essentially a whole model built of a whole bunch of spheres. We're writing like a single pixel, right? You've probably got another one here. They might look a little bit like that. Well, no, they won't. They will still be the same size, right? So the way that I'm imagining this thing is going to work, for the first so many layers, they're going to write like a pixel back. So you get the lines out. So they're going to write a single pixel at a certain MIP, and that will get propagated between the layers, right? Okay, I can just do this, right? It's just save time. Then we can propagate that through the layers. So yeah, this will write like one pixel somewhere, another pixel somewhere, another pixel somewhere, and then it'll propagate it. So you'll get a rough sort of like area where it's like, oh, this thing is, there's definitely a occlusion here at a certain depth value, and the depth value would be somewhere like there, right, for each of those pixels. And it'll be rough, right? It won't be exactly what it is, but it'd be, yeah, it's rough because we want it to be quick. And so effectively, when you get enough of them, they'll eventually cover all the pixels, so the ones behind won't even try to render. That's the idea. Yeah, I'm not sure we're going to keep this thing in the long run, but it's definitely worth testing it out. And also learning from it as well. Rightio, so here we go. So we're going to plug it in now. So when we do the tile binning, we bin every sphere. So let's get some other metrics, shall we? So let's disable the texture. Right, so we're doing about 4.7 ms. Right, it's terrible, but we are seeing there is basically occlusion in a lot of places, except for straight down the middle. It's not liking that, right? For obvious reasons, right? So what we're going to do now is should be able to plug this into the tile binning. So the tile binning goes over every sphere. We've got like 128,000 of these, sorry, 140,000 of these going into, and we loop over and do this atomic add. Loop over all the tiles that it overlaps. Right, so we've got screen tiles, and we are binning a sphere into a tile, and it's going across every sphere. Each thread gets a sphere, and it atomically adds into that tile. And the tile has room for like 256 spheres. It's way too much because we had to have that, and it because it was easily overflowing. It would create graphical artifacts if we didn't. So each tile has 256 spheres pre-allocated, and we're essentially atomic add to insert into that array. So what we've got is this new occlusion buffer. So we can literally just look at the sphere and just be like, are you occluded? If you are, don't bother doing any of this and binning it. So that's going to do two things. It's going to reduce the number of spheres in the bins, so there'll be less to ray trace and check. It's also going to do less atomic adds. So if you have two compute units trying to do an atomic add at the same time, they've got to synchronize across the memory caches, and that's not great. Like it's not good. You get very noisy results. Some frames you won't get a lot of overlapping with your atomic adds, and other frames you get a whole bunch of it, and you just see the performance result. The performance be very wouldn't be consistent. I think the GPU has a lot of ways of hiding this, where it can basically probably preemptively switch to another shader or something. I'm not quite sure on that. So it could probably hide a lot of that latency. But yeah, if so many threads do that, then it could be a big problem. So by checking, so we should be able to take that occlusion right and basically do a very similar thing. We calculate the inner bounds. So I'm just going to copy and paste this code. I should really share it, but let's copy paste it. Yeah, so we calculate a single pixel or texel in the texture at certain MIP, and this time I'm going to read from it. And yeah, it's not the best. We should probably share that code. But oh well. So we'll do something like this, right? We'll say, let's do that. All right, so we also need the occlusion textures. So read only, please. So let's do a compile. Right, S sphere. Let's just keep doing it until it says compiles and we'll fix it. Right, we're nearly there. Sweet. So it's just this we need to fix, right? So get the coordinate. So we're basically getting the inner bounds of the sphere. We'll find it where it's basically 1 pixel at that MIP level, right? So we calculate its size. So if we find its in screen space, we find its bounds. We get its width and height. We find, see this one, it says if it's 0 we return. I think that's fine, isn't it? Yeah, because you don't want to bin it, that's good. Then you get the smallest size. We calculate the MIP level from that size. So this is where this size would be 1 pixel. And then, so we get from the highest set bit, basically. We find the index of the highest set bit, and that would be the MIP level. Yeah. So it essentially gets the rounded down power of 2 effectively. But yeah. Then you get your depth value. This is not what we need. Wait. Yeah, now we need the closest, right? The closest depth value. Whereas we were putting the furthest depth value. Now on the closest depth value. And then we want to then compare that against the one that we read back out. So this is our depth, and this is our occlusion depth. So we do a load texture, occlusion texture at coordinate, and this would be our occlusion depth U. And we say if occlusion depth U is less than depth U, then we know that our sphere is behind another sphere somewhere. So then we can literally just return and not bother binning that sphere at all and avoiding all that work. So that will compile, but we still need to fix up the tile binning. We now need to put in a synchronize on the occlusion texture. And then we also need to put in the occlusion texture base MIP ID. And jobs are good, I think. We won't go out of bounds, will we? Output dims. No, we won't. Excellent. Cool. So let's give that a go. So we should be seeing a massive speed increase. So the top binning is about 0. It's about 1 ms, right? Or 0.8 ms maybe. I don't know. Yeah, it's about 1 ms, right? That's the previous frame. This one's about 5 ms at most, right? So let's sort of see how much better this does. I expect it to be doing quite a bit better. Or yeah, like massive amounts better basically, because we're paying all of this cost, right, to do this. Obviously, it's very negligible, but it all adds up, right? It's a bit like when you go buy all those small items in a supermarket, and you're just like, how do I end up paying this much money? It's like because you just bought tons of items. So, this does add up, but it should knock this down to about 1 ms or less. Fingers crossed. So let's give it a go. Right, so I was kind of close. And we're getting a ton of bugs. So my balls are disappearing. No. So we did save some speeds, but we got some bugs. Some bugs. Oh no. So things are not definitely occluded. Bum bum bum. This is problem. Big problem. So it's saying that the spheres. Because if I did it the other way around. Oh, I should say less than or equal to, isn't it? No, it's less than. Yeah. Let's do the other way around. Yeah, so you've seen the front layers disappearing. And way more is rendering, so it's a lot slower. See, I don't know if it's the resolution that we're doing it at. So let's up it by this to 10,000, see if that fixes it. I don't know, let's do another 200,000. Yeah, I don't know if that's fixing it, not gonna lie. What could the problem be? Like, so you're grabbing a texel and you're like, no, definitely synchronizing on it. Yeah, so you're grabbing a texel for that. Yeah, for that sphere. Oh, wait, we're not taking into account the radius. Do we need to use the outer sphere bounds? I think it might not be taking into account the radius now. So we did the outer sphere bounds, we'll get a pixel. That'd be more realistic, whereas the inner bounds. Yeah, so the problem is the inner bounds is the test you want to do when you're, because it's like this is the space that's definitely covering, and this is the depth value you use, right? The one at the back. But when you want to render an object, you actually want to say the outside of it, put that into screen space, and take the front value and compare, like, because that's the maximum. Sorry, take the minimum and compare against the maximum of the occluded. Of the furthest forward one, right? So let's see if that'll work. Right, I think it's definitely improved. Still got some problems though. I have been seeing it's quite. Should we see if we can replicate? Like, if we enable the debugging, what you'll find is like it's actually quite. See, we're actually animating this very slowly with a sine wave. But we are seeing if you enable the debugging, what you'll see is we're getting this sort of noise here, right? And I'm wondering if that noise is going to persist, or that sort of, yeah, that animation, you know, I guess you can call it noise. The appearing and not appearing. Yeah, so I wonder if oh, yeah. So I wonder if that will go away if the noise goes away, but I still think we'll still have problems. I think you would find the maximum edge. Instead, it's the other way around, and you might want to max the screen bounce. You round it up, so you floor sill. I think it's the other way around. See, that's why Kyrie's use would have been bad actually, because you want to get the find the maximum edge that, and then use that as the MIP. Yeah, I think that could be a fix. Let's disable the debug view. Oh boy, that's eating stuff out of the front. It's made it less jumpy though, I can tell you that, but it's definitely worse. Did you do the Vulkan interpreter? I think it was you working it back in June. No, I did a C to Spear V compiler. So we write shaders in C code now, basically. Yeah. Yeah, something's still a bit fishy. Right, so changing that min for the max fixed that front issue though. Yeah, let's remove the animation. Where's that one? San. The sinful code. Let's remove it. RM sin. Um, it's still animating. It's still. What did I recompile that? It's still animating. Right, so we're still seeing a bit of pop. A bit of this. That's the ray tracer, that's the anti-aliasing thing, I know that for sure. With the edges, something like that. That's fine. Yeah, we're not seeing any of the... We're seeing holes though, we're seeing... Like that is saying it's occluded, but it's not, right? The occlusion there is obviously wrong. See, I don't know... Put it back. I don't know if... Right, so let's think about this then. So you get the outer bounds. Do you want to use the outer bounds? So you get the outer bounds, and you want to see if the whole sphere is occluded. So you round it down. Yes, you sort of round it up, down and up, right? And you're gonna find the maximum edge. And we're looking up on the x coordinate. What do you mean by x? The bounds. Oh no, we don't want to do that. Do you want to look up the middle the middle from the middle? Like you want to get like a midpoint. So you want to say like that plus width divided by 2. And then that means you would have to do that on the other code as well when it actually writes it out. I think so. Well, when you just use sphere, yeah, that's on the screen, isn't it? It's a bit difficult. Nom 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 nom. I just got chewed up. It got chewed up when we did change this min to a max for some reason. We picked the max width and it picked the wrong. Right, that's actually better. There's still some holes there. Oh no, we're missing all of that. I think it got better there, but it way worse there. Oh boy, this is a nightmare. Yeah, you gotta have the animation. Yeah, I can't wait for the type of animation stuff we can do. Like when you move, you can maybe make it sort of like animate, like keep a bit of velocity. Let's see what we can afford first. Could have swore it's got to be a max though. Yeah, but anyway, I think we've learned enough from what we've like, even though it's not working fully, right? So what problems with it working fully? I think we've basically done our, we've like I could spend ages fixing these bugs, but at the end of the day, I don't know if we're going to be using this occlusion buffer. But we've got enough results, right, to start analyzing how good it actually is, right? So I think we should just spend the time now just analyzing how good this thing actually is, and then we can, yeah. So the reason why is because I've got it goes over to the Discord. You see, I got this new plan that we'll be doing, which is to do with like clustering, cluster shading for lights and shadows, based off this learning resources thing I've watched. So if you're interested in about deferred rendering or forward rendering, forward plus, and clustered shading, take a look at this guy. It's a good watch. It's a bit long, but I like long videos. So this is a sort of approach I'm thinking about, yeah, doing next. I'm not sure how close we'll follow this plan, but it'll be pretty close, I think. But I'm not sure if the occlusion buffer can fit into this. And if we've got time today, I might go over it and we'll describe like what we have planned for next stream. So I think let's analyze this data and just see sort of like if it really gets us a win. How much of a win does it get us? And yeah. But we're still taking away some good stuff from this, right? I've learned some things with the whole mip-map stuff, about the odd numbers and that. We've taken away that these performance metrics were actually kind of wrong. They weren't measuring how long a shader was. They're measuring like how long a group of shaders took to run, right, in a weird way. So now we put a synchronization between everything so we can measure a single thing. It's not been a waste. Definitely helped out. No worries, Cranston. Yeah, so I also read this one. I don't wait, no, not this one. This one. Someone showed me this. I don't know if it's you, Cranston. Somebody. Practical cluster shading, which is referenced in that video. And this one goes over. I sat there with my baby on Saturday, and we were both reading this. He was very intrigued. He was just on my lap in the morning while I was just reading it. And it does go over. They talk about tiled deferred shading at 4 plus, and then it's cluster shading. If it just calls 2. It's good. It's a good read, and they solve this problem where they have like a lights off in the distance and how they solve that, which would be interesting to see how they solve it. But yeah, essentially you have like basically screen space, like view space, so frustum tiling. So you can call them like froxels because like voxels in frustum space. So that's probably a nice name to call them. So yeah, it's actually not that difficult to do, and it'll be a bit of fun. So the idea is we want to bin. So you're meant to bin lights in Froxel space, Frustum space, into the Froxels. But I think we want to bin more than just the lights. We want to bin. I want to bin my models and probably my clusters when we have clusters, and then we can probably bin the spheres in there as well. So we can basically have an acceleration structure for ray tracing. But I don't know how good it will be. So yeah, we'll go over that in a second. I just want to. Will you be doing clustered culling? Yeah, exactly. That's it. So we'd be culling. So if you have like a light, yeah, we'll go over it in just a second. So if you have like a light, and you want to render like a shadow map for it, save it in shadow maps. You can basically only select the spheres within the radius of the light. So if we've got a lot, that might be a bigger light there. The bigger the light, the more you have to. Yeah, so we have to think about that. But this seems like the best approach because the problem currently is we do screen tiles, and screen tiles is actually quite bad because the tile would be all of this depth as well, right? So if there's spheres over here, spheres here, spheres here, they're all going the same screen tile. Whereas if you do the frustum, if you do frustum cells or froxels, you basically bin them in an individual cell, and it scales with the it just it kind of scales nicely as well, which is great. Because the stuff far away will probably be quite what's the way to say? But yeah. Anyways, I'll be right back, and then we'll recap on this, see how good it actually is, and then we'll go over the sort of plan for next stream. Right, BRB. Right, welcome back everybody. Got myself a nice big drink. Is OpenGL still standard for hardware accelerated rendering? If you're getting into hardware accelerated rendering, sure. But it's not really the sort of, it's really a crap problem we've got right now. Basically, Vulkan and DirectX 12 is quite hardcore. You have to kind of understand what you're trying to do, and also understand the hardware underneath if you really want to understand, have a smooth learning process. But yeah, so it's basically, you should really be using the newer APIs. They've been around for like 7-8 years now, but they're also for experts only, so kind of OpenGL, or I guess WebGPU nowadays, but I don't know what to suggest, to be fair. Like if you want to learn graphics programming, write a software rasterizer, because then you'd actually understand what goes on. What is this one? Block-free multi-threaded programming crazy. Tiled renderer. Is this optimization only? Oh no, it's not a tutorial. Right, I guess triangle rasterizer. I'm gonna search for. Yeah, this one. So I've linked to this one before. I'm not sure how good it actually is, but it looks like it does a pretty good job. It might be, but yeah, just search for has like rasterized triangles. You basically make a full 3D renderer. It'll be slow, but you understand exactly what these APIs are doing. You have a better idea of what they do under the hood, and then you probably want to look at if you want to learn about how these GPUs work. There's a few places, there's like the Molly GPU tutorials. That's like an ARM CPU, but these talk about how ARM GPUs, but these actually talk about how like a desktop GPU works as well. So that's a good way to understand how GPUs kind of work nowadays. Basically, it's just watch these videos and you'll get a good idea. But yeah. Right, so let's talk about this and see if we can sort of conclude. So at worst, we're paying the price of 1.7, 1.8, 1.9. All right, 0.0. Right, about 0.3 ms for all of that. At worst, right? Because these could overlap. So it's about 0.3 ms for that. For all of that. Then plus another. Let's write this down. 3. And then for all of this propagate stuff, about 0.01, about 0.02. That was up to there, wasn't it? Plus another one of those, that's 4, plus 9, so it gets you about 1.3. Perfect. Then the other one is probably about the same, but because it's just, oh no, it's not. It's I don't know. Um, Yeah, so it's probably about half that. I can't bother to add it all up. It's probably about half that. So it's plus another half. It's about 2. So then this final one. Yeah, we could also just undo it. Yeah, no, okay. This is the bad way to do it. I could just see the total number. I've got it all added up here. We can literally just do this. Right. So here's the total. Let's say it's 3.6. If we literally just disable the occlusion stuff, so we'll just do get rid of all that in the tiler, and then where's all the occlusion bells and whistles here, down to the binner. Right, hopefully it doesn't crash the GPU. Let's have a go. Right, 3.6 to about 6. Which basically means we've got, about 1.8 speed improvement, right, by doing this occlusion thing. So, it does get us a considerable increase in performance, but it's very limiting. It doesn't help us with what we want to do next, which is lighting and shadows. I didn't realize this until I thought about lighting and shadows. But as I said earlier, I wanted to finish trying out this occlusion, this rough occlusion buffer. And I'm glad I thought about the next step, because I would have spent ages trying to fix it and make it perfect. But and just to not be using it. So I think we're not going to be using it, but we might do. So if we are going to use it, we'll just finish the code off and make it work. But yeah, I'm still glad we've done this though, because I've learned a lot, and it's actually fixed my compiler, made my compiler better, so it's been a good endeavor regardless. So we're going to pivot a bit and talk about why we're not going to need this occlusion buffer and what we're going to be doing next stream with the lighting and stuff. Well, thanks. I did a software ray tracer and Phong shading like 20 years ago. Sweet. I was curious about APIs people are using it. Yeah. So if you basically follow those videos on YouTube, you'll understand sort of what the hardware is like nowadays. And then you'll realize when you start looking at the APIs, you realize how kind of crazy it is. You basically, it's kind of nuts. But we're trying to use basically compute shaders, which just allows you to execute effectively, you can kind of think of it as running threads in lockstep and having tons of them that run. You have 32 threads running lockstep, and then you base it on one sort of processor. In a sense, it's not really threads. It's it's a massive SIMD unit. And then effectively you have all these different processors which have executing different shaders or the same shaders. So we're using compute shaders, which basically leverage that and trying to render directly with those, which makes the whole API a lot more simple to deal with. Many universities and indies, I think, use to do is OpenGL. It might be software introduction. Yeah, that's basically what they do, isn't it? I wonder when the support would go from it and what they would do. They might use WebGPU. Yeah, you will have to unlearn things, unfortunately. Yeah, it's good at learning the high levels, but not really anything to do with how the GPU actually works. Yeah, it's a good take. So, why is the rough sort of occlusion buffer? Right, so you can think of it as like a little rough occlusion, right, where there's like a depth valley that's going here, but it's not really representing what's really going on. But you imagine if the whole screen is covered with spheres, right? And you're saying roughly the occlusion is here, so anything behind this line can be discarded. That's what we was trying to kind of achieve, but it didn't really work out, as you can tell. But and we had some bugs to fix in the performance. It wasn't 10 times better. It was 1.8 times better. So it wasn't, which is still a good win, but it's not something I was looking for. Okay. Maybe we won't be able to get that big of a win, but it's also got another problem. If we're trying to render lights, it's going to be a big issue. Why is it a big issue? So let's draw another frustum. Get some lines. Back here, yeah? There we go. Jobs again. So here's our near plane. Bum, 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 bum. So we got ourselves a sphere, because it's just the easiest thing to draw is a sphere, rather than many spheres. And then what you have is another sphere here, and you have another bigger sphere here. Now we had that occlusion buffer, right? So we would say, oh yeah, the rough occlusion is something like this, right? So we would, the idea didn't quite work out, but the idea was I could check, this sphere could check against the depth value in the occlusion buffer and be like, oh yeah, I'm behind there, so I'm occluded, so don't bother rendering me, right? But this is a problem when you have a light. What's the best way to draw a light? This is a light. Ta-da! So you have a light here. It's going to cast a shadow right onto this. So when you sample, you shoot a ray out. Bum 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 bum. You hit that pixel. You want to check if you're in shadow or not, right? So you can cast rays. You can you cast rays and check against every sphere, or or you can do like a shadow map type deal. But so then you can't when you're rendering the shadow map, or when you're doing a test against these spheres, you can't be using the same spheres which were you have to include the spheres which even will be occluded, right? Because if I know this sphere was occluded and I got rid of it from any acceleration structure, like we have an acceleration structure right now inside screen space. So we split this into tiles of like 8 by 8 or 16 by 16, whatever it is, pixels in screen space. But you can think of them as on the view, on the near plane, right? So we would have like this one here, and this one would point to like an array of one item, and this item would be this guy, right? This sphere. But so it means we'd need another acceleration structure anyway, which doesn't have this occluded information. Occluded spheres that are not occluded. So it kind of, the occlusion buffer doesn't really serve any purpose other than the final render. So what we kind of want is something that will be an acceleration structure that will help us make shadow maps, but will also help us with the final render, and can also help us with what? So it's not just shadow maps, probably lighting in general as well, doing all sorts, doing diffuse and maybe specular lighting as well. So we could probably do ray tracing and yeah, so I'm not sure, honestly, I'm not sure about the performance of this stuff, how it's going to be. I think yeah, we could try our best, but we might have to make the sphere size quite big for some older hardware, I imagine. And maybe just use shadow maps, and maybe we can cache the light into some other acceleration structure as well. We'll see. So this is what we'll be exploring next, basically, is this other acceleration structure. So we want to basically do like a forward renderer. Like we don't do a deferred renderer, where we basically, you know, sorry, I'm just spelling stuff all wrong. Deferred renderer. Oh, G buffer. Right, put into a G buffer. So what is a G buffer? Essentially, you break things down into about 3 or 4, maybe more textures. I think there's a good video if you guys want to, want some content. I got you back. I got videos for days. It's not me, right? Jasper, Legend of Zelda. So there's a bug in Legend of Zelda, and Jasper sort of goes over it. This one, and it talks about how the architecture works for the Legend of Zelda, on the Switch. And it talks about it, spoilers, there's G buffers, and there's like 9 of them, or whatever, and there's more. And it goes about each individual one. I didn't realize the Switch hardware could deal with 9 G buffers, but anyway, highly recommend watching that video. It's actually really, really good. I might actually watch it again because it's that good. But essentially, you render your scene once, and then when you're rendering it, you put it into, when you're rendering each pixel, I think, you put a pixel into 3 to, I guess in that case, 9 textures. And they could be for whatever you want, but people typically do the color. So like the base color of they do the base color of the object. It's called the albedo color. So this is before it's lit. Like, what is the surface going to give you? The normals. So the surface normal. So sure, we all know what surface normal is, but the surface normal would be like an arrow pointing away from the surface, right? Like that. And you can use that for shading, right? So yeah, all of this stuff is used for shading basically. And then you got like position for some reason and depth. I'm not sure why you'd need position, but that's what that's done. But you could do more stuff like basically metalness, roughness, and do the full PBR thing, right? But yeah. But there's kind of issues with doing it this way. Like the biggest issue is you don't get transparency. Because you're basically flattening it into a texture. So you don't get layers. You don't get... So when you do your lighting, you don't... So the lighting happens after this step. So this is probably a good image for it. You basically render out these 4 images. Yeah. So probably learn OpenGL is another good resource. You render out to the 4 images, and you basically... sorry for the white screen, but it's going to happen. You run out to these 4 images, and then you basically run over a full screen, and you basically light it. There's also some other issues and stuff that I won't bother going into. But yeah, we don't want to be doing that. So if people are familiar with that, we don't want to be doing that. So we want to try and do like a forward approach. And there's basically this, I've linked to this earlier in the chat. This sort of like clustered shading approach. So the problem with forward rendering is that there's not anything that's cached. So forward rendering means when you render a pixel for a sphere or something, you want to light it there and then, and so that means you can deal with like transparency. There's obvious downsides to it. Like imagine if I render them out of order, which is not going to happen in our case because we're going to trace rays, right? But say if I render this pixel on the screen down there, and I light it, and then I render another pixel here, and then I light this one, and this one overlaps that one, and it is in front, so it's, you know, goes ahead. Obviously, you've paid the cost to light both these pixels, but you've only used one, and you do that for all the pixels that overlap. It gets kind of expensive doing the calculations for the lighting. So you have that overdraw problem. But we don't really have the overdraw problem because we're doing ray tracing. We're going to sort them, but we're going to have different problems because we're going to ray trace. Okay. So the basic idea is you split them into these sort of like frustum cells. You can call them like froxels, basically. That's a nickname that's you can call these things. It's actually not too difficult to do this. The maths is actually quite easy. Like, you can figure out these. So this can fit in a 3D texture. And the beauty is you know, if I was to not do it this way and do it in world space, so this is in frustum space. If I did it in world space, you would go like, maybe it's better to draw it. You would, if I did it in in world space, you would have all this wastage of cells outside the frustum, right? Well, probably up to here, to be honest, but you see what I mean. You have all this wastage here of cells, and they wouldn't really reflect the projection that you get either, right? So it's not good doing it this way. So instead you do it with frustum space. So essentially you want to bin. So the way this clustered shading works is they'll bin the lights. It's all about binning lights, and yes, this is meant to be basically like, oh, we've got a light, and what is this picture? Yes, I think there's an optimization here. We need the min-max depths, so you can not bin any lights that you don't need or something like this that you render. There's something I need to look into a bit. But the basic idea is you bin the lights into the cells which the lights affect. So you basically have a smaller list of lights to look over. So you're essentially caching, right? So if I want to, this is going to take ages, but essentially like you have, you know, point lights and spotlights. So the point lights could probably be a sphere, and the point lights you could probably do another frustum, like a frustum verse plane. Yeah, right. I think this is getting good. So you got your like froxels, right? So you have like basically this light affects all of these cells right up to here. So that means you bin that light in all of these cells. So when you try and light a pixel in this cell, you just look up, you have a list of lights that affect this cell, and you just look at that light and see if it's, you know, you get the shadow map for that light, see if you're in shadow. If you're in shadow, then, you know, I'm in shadow. So you don't have to, if you have many lights on the scene, you effectively avoid doing calculations for lights that you don't have to. So essentially it's a way of caching the lights. And that's all this clustered rendering, clustered shading is. If you watch that video I linked earlier, it does a way better job of describing all the methods. What else? Light is pre-processed. No. Yeah. So that's a good point. Yeah. So if you were to use a shadow map, it could be one of two ways, right? For the speedy implementation, we'll probably do shadow maps with like worse quality. But then for more high-end GPUs, we'll probably do ray traced approach. So the ray traced approach will then, I think we're going to bin. So we'll do something different from the clustered stuff. We're actually going to put our spheres in here as well, in these voxels. So we'll have a list of spheres. So we'll actually cast a ray, and the ray is going to go through these voxels and get a list of spheres and check if it's hit a sphere. If it has, it's in shadow. If it hasn't, it's hit the light. Right? Yeah. So there's definitely some optimizations we can try and think of from this. I'm not quite sure. Like we can maybe see if whole voxels are occluded, basically. It's quite, yeah. Like if you have a massive sphere covering a whole voxel, maybe. Yeah, so it depends if we're doing ray tracing or not, basically. But if we're doing shadow maps, then we'll have a pass which pre-renders a shadow map for each light, and that will just look at the spheres in those voxels, and then only render those into a small texture, that sort of thing. Yeah, it will record a depth value into that texture. So you can look up the depth value and see if you're occluded, basically. Wait, see if you're in shadow or not. Right. Yeah, so I've still got to go into the whole yeah, why is this better than tile approach? But yeah, hi Andela, how's it going? I have a question. We get variable number of lights per pixel. Won't it mess with wavefronts? AKA pixels in a wavefront will have different amount of lights to compute. That's a good point. So you've got yeah, it's not something I thought about. So you've got, okay, so you shoot an array, hit a pixel. Yes, so you are going to get, that is quite possibly true. You're going to get different lights. So you'd have to try and, yeah, but hopefully they're kind of the same. So when you shoot your rays a pixel apart, some of them are going to be next to each other, and therefore they'll get the same lights. But others are obviously going to be so different, like completely miss or land in a different voxel, and you'll get a different set of lights, potentially. Yeah, you'd have to search in a different set of lights. And if you end up in a different list of lights, you would then pull in a different list. But and then essentially the indices could be out of in a different order, so you could have the same lights. So you might be better off to sort the lights. No, but then if you have... No, that wouldn't be good, a good one to do. Because then if you... Yeah. Yeah, it's a good point. I need to think about this one, because there might be ways to make it better. A tile classification pass to remedy that, could you? Yeah, so another thing that I've seen with this... I've seen something with this, I'm not sure if you guys have been aware, but there's another thing called like screen space shadows. There was a video done on the PlayStation. Oh, I forgot when it was now. When the GDC was going on. Was it screen space shadows? See, it's hard to find the video. It's actually really hard. There's like a Sony Expo base. I don't know. There's like a Sony thing held next to the GDC, and someone talks about screen space shadow. But anyway, the takeaway from that is he launched one ray, and it done 32 threads for one ray, and it compared. It used the 32 threads to do 32 comparisons at once or something. Wait, what was it? It did 32 lookups, and then it would do something with those values. It would like share them or something. But I was thinking with maybe that could serve a purpose for here. Where you could go, you could compare. Yeah, but if it's so if you got 32 spheres in a Froxel, maybe if they're really small, you got 32 spheres in a Froxel, you could do 32 checks at once. And see if you hit any of them. For one ray. And then that way, when you do a hit, and you did a test against each light, you would be sharing, you would go over all the spheres or something. If you did ray tracing at least fully. But if you did a shadow map, you would probably be wasting 32 threads. No, because you look up 32 different lights at once. Yeah, so maybe you could do something like that. And you could do... Maybe that could be an improvement. But yeah, that's a good question. Have you found the video, Cranston? Yes, this is it, this is it, this is it. Yeah, screen space shadows. Yeah, so this is a good talk. Basically, it's all about adding extra detail into a scene, like all the micro detail into a scene using screen space shadows. So it's meant to be like an assisting. It's actually dirt quick as well. It's like 0.3 ms or something for the whole thing. It's dirt cheap, and you basically get to like add all this distant shadow in the scene or something. It's pretty sweet. So all that in the background just gets shadows if you flip it. Oh, okay, maybe not. No. Okay, but yeah, see, it uses this depth and where's the yeah, there you go. So the before after, basically, which are not really can't really be done with shadow maps. Oh, I need to not lose that video because he actually gives the source code a way we can just use. It's on the learning resources now. Right. Thank you, Cranston. Good fun. But yeah, that's a good point. I need to think about how we do the dispatch on that. Yeah. Because if we have a high number of spheres, maybe that's a good way to do it. And a high number of lights. But anywho. There could be a lot of wastage though if there isn't that. Okay. So also another benefit to using why you do this sort of view space binning is maybe I did say this earlier actually, but the whole point is like I think there's another approach called tiled shading, and it's kind of what we've done right now. We basically bin stuff into screen tiles, but that is obviously problematic where if you bin them, you know, like these two spheres end up in the same screen tiles, whereas when you bin them based on these, they don't. And if you have 100, you know, if you have like 100,000 spheres or whatever you're gonna have, that's a lot of overlap. Or if you have, you know, loads of lights and you bin them into the screen, it's you don't want to be binning extra lights that you don't need to. So you might have another light here and another light here and another light here, just to keep it simple. You'll be binning like 4 lights. Well, those lights, imagine if these go like across the whole screen for some reason, right? You shouldn't really be doing this, but imagine if they did. They would be going in basically all of the pixels, right? All of the screen tiles. But if you do it this way, they'll only be going inside the Froxel grid. They'll only be going inside the grid. Not sure how this is really going to be done, but yeah, they'll only be going in the grid cells that they actually overlap. So that when you try and get a light for a pixel, you should hopefully have less lights to look over, right? Yes, that's what we're going to be doing in the next set of streams. So we're going to be starting off with this sort of Froxel space binning. Has anyone got any questions they want to answer quickly around this? So it's actually quite easy to do the binning. You know, you might be thinking, how do you do like world space versus a sort of a Froxel, like it's a really odd shaped box? Well, the way you do that is you essentially just do, I think you can get away with like 3 plane. Here's the thing. I think you can get away with essentially 3 plane versus, you know, sphere or whatever it is, right? Whatever thing you're testing against. You should just be able to do 3 of them. In 3D, but you might have to do 6. So it's plane versus sphere. I think you only need to do 3. So you have like your, let's just do a, so here's part of the grid, right? Something like that. So you have your sphere, and you essentially just say if it's yeah, the simple test is, you know, if it does your sphere go in this cell, or if it does it collide with this one? No. Does it collide with this one? Yes. And then you basically just bin it. But you know, that's 4 in 2D, but it's kind of like yeah, 6 in 3D. But I think you can do, I think you can get away with doing it a lot quicker. I think you can effectively do 3 sides. And you can do it into local space or something. It's something weird like that. You can... See, I'm not quite sure because these planes are different. They've got different normals. Ever so slightly different normals. So maybe it's not possible. You might have to test against 6 sides. Maybe there's an optimization there we can do. I don't know. But yeah, that's the basic idea. So I think that's what we'll start off with, is basically binning. I've got a whole sort of thing on the Discord if you guys want to check it out. Where we go over the sort of plan. And after we've done the binning, we're going to change our rendering to use this voxel grid instead of the screen space grid and do the rendering that way. And then after that, we're doing the lighting where we get some lights. We'll bin those, and then we'll figure out, I think we'll just do the ray traced lighting because it's the easiest to do. Yeah, it should be the easiest to get some form of lighting going. And then after that we'll do the shadow mapping, I think. But yeah, rightio. Okay, so I'll upload this code onto the GitLab for those who have the code. Anyways, so I'll next be streaming on Tuesday, 6:30 p.m. GMT. So for those who are around, there's that one. There's also Thursday 8 p.m. GMT. We'll just be working on all that good stuff. Cool. Yeah, we'll probably do shadow maps, but not right away. So I have a Twitter here. Follow me on. There's also Discord, as I said. And you can also get access to code if you subscribe via Twitch or Ko-Fi. Ko-Fi is much better for me because it's Twitch takes a lot more of the percentage. So yeah, appreciate it, guys. Appreciate you all coming. Yeah, shadow maps, we'll probably roll those for the sort of cheap solution. Unless I can think of anything else until then. Because there's some ideas, right? I think the classic stencil shadows gets you like nicer, crisper shadows, but that involves like meshes, I think. I have to think about it. I have to do some research. Yeah, so those will be what's the word for it again? I keep forgetting this word. A book here which goes over it. Not that I read it. Cascaded shadow maps, that's the one. Yeah, you probably want to go cascaded, right? But yeah, it's still got problems. Yeah, cascaded. Like you'll probably start off with a shadow map and then just do cascaded shadow map. But yeah. What book? I don't know if I can recommend it, to be honest. Yeah, I'm not sure if I can recommend the book. I don't know if I want to recommend it. It's good. It goes into a lot of detail. But yeah, it's not. Equally, you could just find the stuff online. Yeah, I don't know if I want to advertise it. I'm sorry. I don't even want to suggest it, to be fair. No, it's not the OpenGL4 one. It's more of a general rendering one. Boom, boom, doom, doom. Right, oh, we found someone to raid. Yeah, Lone OpenGL is a good way to go. Just, yeah, go there. If you've got any high level rendering stuff to do, Lone OpenGL is pretty good. Right, yeah, have a good start to your work week, everyone. I'll see you all on Tuesday. We're going to start this. This is going to be pretty exciting stuff. Actually, try something different. And also should deal with our lighting situation as well, hopefully. So yeah, see you all very soon. Thank you for coming, and catch you later.